Good morning, everybody. It's my pleasure to introduce the first speaker of today, Anna Skorobogatova from ETH Zurich. And her talk is the first part of a mini course. The title is Regularity of area minimizing and almost minimizing kernels. Please.
Yeah, thank you very much, Alessandra, and thank you for inviting me. It's a great pleasure to be here. Yeah, so I'll talk about regularity, the area minimizing, and almost minimizing currents. So I'll start with some background. So for those of you that are already familiar with currents, it'll be a bit boring to begin with, but yeah, bear with me. Yeah, the guiding question is, of course, the plateau problem, which in the most classical case is asking to look for surfaces of least area spanning a given boundary. But we need to make this question well posed. So my surfaces are m-dimensional. My boundary is m-1 dimensional, and this is always for simplicity, because I'll focus on the regularity rather than existence, where, you can formulate everything in a sufficiently regular ambient Riemannian manifold, but I'll take this to be, I'll take it basically to be Euclidean space with a Euclidean metric, because, yeah, for regularity, when you everything involves localizing heavily, and then you just get sort of extra error terms coming from the ambient manifold. For existence, it really does matter, but yeah, not for regularity. And yeah, the first question is, which framework do we want to use to solve the plateau problem? And there are a number of natural frameworks, starting with most classically Douglas and Rador, which is a kind of parametric approach. The 2D surfaces, and R3, and yeah. And then, right, but this doesn't generalize easily to higher dimensional surfaces. And so in arbitrary dimension and codimension, there are broadly two natural frameworks, one being the set theoretic approach, kind of pioneered by Reifenberg with his topological disk theorem in 1960, and then using this kind of Czech homology, whatever that is, but then kind of, yeah, Reifenberg's approach didn't really cover all possible, it was somewhat restrictive as to which kind of boundaries you allow, and yeah, what kind of behavior surfaces can have. And somehow more natural set theoretic approach came a bit later. So yeah, there was also, I guess, firstly there was Almgren with his minimal sets, I think 76. But then sort of more recently it was Harrison and Pugh, and Delelis, Margie, Geraldine, other way around, Delelis, Geraldine, Margie. I think this was 13, 14, where they sort of, in the set theoretic world you can make, because, right, you need to make sense of, somehow this problem comes with an orientation, of course. So you need to make sense of what it means for your surface to span the boundary. And using sets, they did this using, there's like a homotopic spanning condition. Using sort of homotopically closed families of loops, for instance, for hypersurfaces, that you want all of them to intersect your surface. But my focus here will be the functional analytic approach. Pioneered by Giorgi and in the 50s, and it was Federer Fleming who yeah, I'll revisit this in more detail. It was already mentioned yesterday, but they got the existence result using these currents, which will be what my notion of surfaces will be throughout. And right, so yeah, so for throughout my, so this will be this will be the framework I focus on here. And yeah, so what are currents? Let me remind you. So and yeah, within this framework, there are sort of two natural classes that give a reasonable regularity theory, which will be my main focus. One is area minimizing integral currents, where you're taking integer multiplicities, which probably a lot of you are very familiar with. But I'll also discuss a bit these currents mod q, where q is a given integer and you're taking multiplicities modulo this fixed integer. So I'll discuss that approach a bit as well, which is also kind of natural, because one drawback of using integral currents to solve the plateau problem is that the regularity theory you get is you get I mean, okay, for hypersurfaces you can do better, of course, but for arbitrary dimension and codimension, you get a codimension 2 singular set with respect to the dimension of the surface. And sort of in general, we expect like actual soap films, which is sort of what the plateau problem is supposed to be representing. They have codimension 1 singularities like triple junctions and things like this. And using these mod q currents, you can, for instance, mod 3, you can see triple junction singularities. So it's kind of a more natural approach from that perspective. And the techniques for the regularity are pretty similar in general. I mean, kind of the main takeaway is that essentially these mod q area minimizing currents will have basically this extra piece of their singular set that is exactly codimension 1, as well as what you see for classical area minimizers. So and an m-dimensional current, which I'll denote by T, Rm plus n, or an open subset, is, so it's a continuous linear functional on the space of smooth compactly supported M forms. So these are And so, yeah, so already in this full generality, which we don't want to work with, we'll very quickly restrict ourselves to, mostly I'll focus on integral currents. So we'll very quickly restrict ourselves to that setting. But already in this setting, you have, so this is equipped with the weak star topology induced by this duality. And this gives you a well-defined notion of boundary and mass, right? So it acts, if you boundary on an m-1 form is defined to exactly generalize Stokes' theorem. So, you know, you could always bear in mind that a smooth oriented m-dimensional submanifold induces an m-dimensional current acting by integration on m forms. So if P smooth oriented, then you have the kind of canonical multiplicity 1 current that is associated to this guy that is just defined by integrating. And so, right, for these guys, this is exactly Stokes' theorem, and in general, we define it this way. Yeah, so we also have a well-defined notion, as I said, of mass, which is just the, right, as you would expect, by duality, you take all m forms, most one. I use this notation. Okay. But right, working in this amount of generality is not a good idea because, I mean, if you like, you can think of currents that they generalize m-dimensional surfaces in the same way that distributions generalize functions, and indeed, zero currents are distributions. But right, just because the current is m-dimensional, I mean, we want it to still represent an m-dimensional surface in a suitably strong way, even if it is a weak generalization. And just because the current is m-dimensional, it doesn't mean that it will have m-dimensional support. So, right, I mean, by the Riesz representation theorem, and we'll always assume that our currents have locally finite mass. So if, let's say, finite mass even, there exists a radon measure, a vector-valued radon measure associated to this current, which takes values in the space of the, in this like wedge space, right? So it's, I never remember what the subscript or superscript. Right. So you can find an associated radon measure such that you can represent your current as, so this is my M form. You have the kind of polar, which is the vector part, and then you have the mass part. So, so maybe I'll write this as, right, you can take the polar decomposition. So I'll write it like this. And then here you have. Okay, so we have this sort of associated radon measure that we can take, but this measure will not generally have m-dimensional support. I mean, you can cook up whatever wild examples you like where it's supported on, say, like a Dirac or something, despite starting with an m-dimensional current. And so, right, this is why we want to restrict ourselves. If we want to have like a reasonable coexistence and regularity theory, we restrict ourselves to those currents that still have nice support. So you have the integer rectifiable ones, where this radon measure has rectifiable support, and you're weighting it with a locally integrable integer valued density function. So we restrict ourselves to integer. But first, say the integer rectifiable currents, and then we'll immediately take integral currents where we have integer rectifiability of the current and its boundary currents. So these are those where the support of, say you take this guy, is, or maybe I'll write it, okay, I'll write it like this. So you can directly write it as mu t is, you have some function here, which I'll, how do I want to denote this thing? Let's see, say tau, no, tau is my tangent plane. Okay, so I have some function k of x, which will be L1 log integer valued. And then I take this to be, so this will be the oriented simple M vector associated to, so I'll take the support to be this M rectifiable set. So at almost every point, you have a well-defined tangent plane that you can orient. So this will be the associated simple M vector to this tangent plane. And then I take the M-dimensional Hausdorff measure, restrict it to, so this is an M rectifiable set. Okay. And so, right, we also, I mean, yeah, we also want to have good behavior for the boundary. So further pick integral currents which are such that both T, so T is M, integer rectifiable, and the boundary is M minus 1, integer rectifiable. And yeah, I mean, implicitly in all of this, I'm taking the mass to be finite. So actually, you can get an integral current if you just, I mean, it's enough to ask actually that additionally the mass is finite. So that's another way of characterizing this. Yeah, so these will be my surfaces, at least for now, until I digress a bit and discuss these mod Q currents, which will basically be, you take integer rectifiable ones and then you'll consider representatives in the flat topology with mod Q coefficients, but we'll get into that soon. So for now, we'll focus on these integral currents. And yeah, this is a reasonable framework in which to, for a start, get existence for the plateau problem. So right, so better Fleming showed that there exist solutions to the plateau problem in this class of integral currents, meaning, so maybe for, so I don't have to keep writing this, I'll always say that T is IM plus N. Okay, and yeah, maybe I'll just say, like, it's reasonable to take, yeah, I mean, for a start, it's reasonable to take integer multiplicities here. I mean, you could naively try to first take, like, say, real multiplicities, and sure, you can get existence kind of much more easily even by the direct method in that case, but saying anything in the direction of regularity is very hard with general real coefficients, and in general there's a Lavrentiev gap. So there's a if you solve the plateau problem over currents with real coefficients instead of integer ones, then you can get strictly smaller mass. There's I think the prototypical example is like involving taking your boundary to be a curve on the Klein bottle, and you can consider basically the or rather a bunch of curves on the Klein bottle with sort of alternating orientations, and you can show essentially if you look at twice this guy, then if you look at the filling area of twice that guy, it's strictly smaller than the filling area, than 2 times the filling area of that guy. So, but yeah, so basically, yeah, it's reasonable to take integer multiplicities, and this is also, right, but, and in general, we do want to take not just multiplicity 1, because you can have all kinds of, right, for compactness purposes, you want to consider when things collapse and you form higher multiplicities. So, you know, if you solve the plateau problem with this boundary where you're orienting both disks, both circles in the same direction, you'll get 2 disks. And as you push one down, you want to say that in the limit, you expect to see 2 copies of one disk, and you want to keep track of phenomena like this. So really considering integer multiplicities is something we want to do. And yeah, so in the class. And so yeah, better affirming showed that you get existence, meaning sort of in the integral homology sense. So I mean, in our in ambient Euclidean space, you kind of don't have to formulate this homologically, but in general, in an ambient manifold, it's kind of the only reasonable way. So right, given a boundary gamma m minus 1, which is a m minus 1 dimensional integral current, there exists T, which is a m dimensional integral current with boundary of T being gamma, and if you consider the mass of T and you compare it to the mass of any competitor in the same integral homology class, then T does better. And here R is n plus 1 dimensional. Okay. All right, so yeah, so we have a good existence theory here. But as I said, my focus will be regularity. I just wanted to convince you that this framework is reasonable. And so to that end, we so right, so I guess the starting point is to make sense of what we, yeah, so from now on we'll discuss focus on regularity. So right, the first thing to do is to define what I mean by regular and singular set, or remind those of you that are already familiar, I mean, often it kind of depends on the context, how you define the singular set. And here we take first the regular set to be all the places, all the points in the support. So the support of T being the support of this measure associated to it, such that you have a neighborhood around this point where the support of the support of the mass part of this measure, so it's sitting on a smooth submanifold, and you're weighting it with, I mean, essentially by the constancy theorem, you can say that, yeah, then locally around this point, you really have this smooth guy with a constant integer, positive integer, sorry, a constant integer multiplicity. Okay, so there exists neighborhood U, such that T restricted to U is supported on a smooth m-dimensional oriented submanifold. And yeah, as I said, this then at the level of the current itself, you have this guy with some integer multiplicity. And then we define the singular set. And of course, yeah, boundary regularity is also a very important question, but my focus here will be on the interior singular set. So I'll define this to be the support complement the regular set union the support of the boundary. So I'll always be localizing to where the you don't have any boundary for your surface. Okay, so now, right, maybe let's start with some classical examples of singularities that really exist in this framework. So I guess the one that we're probably all very familiar with is for hypersurfaces, you have Simon's cone. Which is, right, it's the cone over the product of three spheres, or if you like. And this sort of sits more generally in a class of Lawson cones, which are, yeah, more general variants of this, which are all area minimizing, starting from when the cone is 7-dimensional. And yeah, so this is, it has an isolated singularity at the origin, and Bombieri, DeGiorgi, and Giusti proved that this was minimizing. And then, yeah, since then there was also a much simpler proof because, yeah, I mean, their proof essentially relied on looking at the symmetries of this cone and reducing the question to solving an ODE. And yeah, so, but then since then, there was a method using sub-calibrations, super calibrations by Philippis Paolini, which is kind of relevant because I'll soon talk about calibrated and so-called semi-calibrated surfaces, which will be my almost minimizing ones that I can say that I have a good regularity theory for. And yeah, so okay, so that's the codimension 1 example, where we have a much better regularity theory, as I'll shortly discuss. And then in higher codimension, we have a whole class of examples coming from holomorphic curves or yeah, holomorphic subvarieties in general, so higher dimensions, holomorphic, which we'll see why they're minimizing in a minute. So for instance, I guess the most classical one that everyone writes is if you take WZ to be my complex variables in C2, which I identify with R4, I take W squared equals Z cubed. And this gives me an important example that we'll keep coming back to throughout, because so somehow this example is really like a non-flat singular cone. But these examples, there are a bunch of them that contain singularities of this type, where you have, so if you think about what this thing is doing, it has a branch point at the origin. And this is, yeah, an important sort of obstacle to consider. And when probably in the second half of the course, I'll discuss the ideas behind Ambron and Delella-Spadaro's proof for Ambron's big regularity theorem. The main difficulty to say anything about the size or structure of singularities for higher codimension surfaces. So maybe a lot of people are familiar with the codimension 1 theory, where things are much nicer because so in codimension 1, we have cheating, meaning that locally, when you look at, so if T is a m-dimensional integral current in Rm plus 1, and it's boundaryless, then locally T is a superposition of boundaries of sets of finite perimeter, which are top dimensional currents. So these are sets of finite perimeter, which, yeah, it gives you this sheeting structure for hypersurfaces, which allows you to go down to a codimension 7 singular set. So you can do much better. And the point is that, yeah, this so this means that in particular, and we'll revisit this sort of more precisely soon, but one cannot have singularities with which the surface is very close to flat. So yeah, we'll next talk about the monotonicity formula and consequences of monotonicity for mass ratios and consequences of this for blowups. And the point is that at the level, like, you use this monotonicity formula to take tangent cones, and you can then use it to stratify the singular set. And the point is that somehow the main obstruction towards getting some lower dimension estimate on the singular set is the possibility of having singular points where you might have at least one tangent cone, one blow up that's supported in a flat plane, which is bad because this kind of tells you nothing at the level of stratification. And also, if you like, at the level of like Allard de Giorgi regularity theorem, also you can't hope to get this kind of epsilon regularity theorem type conclusion, because your surface will be close to flat there, but it still has a singular point. So it cannot have singularities where T is But for hypersurfaces, this doesn't happen. For minimizing hypersurfaces. Okay, and so in contrast, in higher codimension, we'll also see that for these mod Q currents, actually, yeah, for already for hypersurfaces, one can have these kind of so-called branch points where this falls apart for these mod Q currents that we'll see later. But for integral currents, so for integer multiplicities, this is true for hypersurfaces, and in higher codimension, you can have branch points, as depicted by that example. And if you consider what's happening there at the origin, you have these kind of two sheets of your surface, and they're collapsing together tangentially. So I guess when I talk about this stuff and I have slides, there are very nice pictures, at least of the real part of this guy. I'm not going to attempt to draw this, but yeah, I mean, the idea at branch points is you have this kind of tangential collapsing of more than one sheet of your surface, and you get necessarily higher multiplicities forming. Okay, so how are we doing for time? Am I supposed to take a break at some point during the... Okay, maybe I do it in like 15 minutes or so. Okay. All right. So right, the starting point to analyze singularities in general and yeah, after I mention this, I'll also mention the sort of important class of area minimizers that we want to consider, which will bring me to these almost minimizers, which will be calibrated submanifolds. But yeah, let me first just to remind you and sort of to yeah, like coming back to when I'm saying T is close to flat, we have monotonicity of mass ratios, which tells us that if you look at the difference between two, so this is the volume of a unit M ball. So you look at the difference of two mass ratios between two scales at any point, then you have an explicit non-negative remainder term, which is given by in the annulus. So R will be, so maybe I write R of Y X. M. So you have this explicit non-negative remainder term, which, yeah, in particular tells you that and this is really for all points, right? Which tells you that in particular, the density, the M density exists at every point for your surface, you can use this monotonicity to take blowups. So this limit R goes to 0. Yeah, this exists. And another consequence of this, which you can see from sort of analyzing this remainder term, is any subsequential limit of rescalings, any subsequential local limit in the weak star topology of these rescalings T X Rj, where this is you push forward under the map that, right, so you take B Rj around X and you rescale to the unit ball. So this is the push forward under this sort of rescaling map, which I'll denote by iota X Rj T. So this, any subsequential local weak star limit of these rescalings converge to an area minimizing cone, meaning that this limiting guy is invariant under dilation under rescalings about the origin. So meaning that iota 0 R, if I call this C, but this cone, right, this is a cone depending on the sequence, the subsequence of this, which is very important. And yeah, I mean, in general, it's still a wide open question as to when we have uniqueness of these so-called tangent cones. Because yeah, a priori, you can get potentially very different things along different sequences of scales. So you always know that this thing is going to be conical, but maybe, and yeah, I mean, in this particular context, I don't know of counterexamples, but in other contexts where you have kind of other monotonicity formulas, you can produce examples where you have some kind of rotating behavior with the scale where you see a different kind of cone. I mean, I don't know of anything too wild where like the topology of the cone changes drastically, but you can produce examples of non-uniqueness in kind of analogous contexts to this in general. And kind of what we'd like to do, so then kind of what we'd like to do is understand the size and the structure of singularities by, I mean, the first naive thing one can try is to basically study possible blowups, so possible tangent cones. And indeed, that's what we'll do, but let me first briefly digress to these almost minimizers that the title of my talk promises. So the next thing to try will be use or maybe study tangent cones at singularities to see what information they tell you about the singular set. And it will turn out they give us some information about the size and structure, but these branch points will always be a problem, at least if the goal is to get some lower dimension estimate and structural result at a lower dimensional level for the singularities. T. But first, I kind of want to do this before I erase the monotonicity formula, because the point will be that, yeah, we still, so for almost minimizers, we can still get something analogous to this, and we can still take blow-ups that will be still area minimizing cones. Because, yeah, the point will be that our notion of almost minimizing will be so that you're minimizing up to a higher order error term. So then you can do the analogous computation that wants to, right, to derive this. I mean, there are two ways to derive this. Because you can even derive this more generally for stationary, so for critical points of the area in the framework of stationary integral varifolds. So you don't need the minimality or the orientation by essentially testing against a radial vector field. But you can also derive this specifically for minimizers by comparing to the competitor, which is a conical extension of the boundary data of your surface on the boundary of a ball. And the latter is sort of the thing one can repeat for these almost minimizers that I'm about to introduce to get essentially a formula like this plus a higher order error term that will go to 0 as we take the scale to 0. So it's good for blow-ups. I mean, for blow-downs, not so good, but for blow-ups, it's good. Okay, so to start talking about almost minimizers, the first thing one wants to discuss, and the reason to consider more general almost minimizers is because, right, I mean, when it comes to like actually verifying that something is really minimizing, like it's a pretty rigid condition, and generally we only know how to do this in kind of very specific ways. So I'm about to introduce the notion of being calibrated, and that's kind of the main tool we have to check that something is really minimizing. Yeah, unfortunately, being calibrated is like even stronger than being minimizing. You're minimizing with an extra sort of special structure. And this isn't very flexible. So it's not, you can't expect this in general necessarily, but you might expect in a number of contexts that you're minimizing up to some suitably small error term, like suitably small at small scales. And a good class of these almost minimizers for which one can recover the same kind of regularity theory as you get for minimizers will be these so-called semi-calibrated surfaces, which they're not just almost minimizing, they'll be almost minimizing with a very specific error that still gives rise to a PDE. And we'll also see very briefly that for very general almost minimizers, you basically can't expect any regularity theory. So kind of, although the most general notion of almost minimizing in the sense of allowing a higher order error is, yeah, I mean, it's, you might think that this is something desirable. Yeah, for the purposes of recovering good regularity, you want to make this, yeah, you want to ask for a bit more from this error. Let's start with calibrated, and this brings me back to the reason why this class of holomorphic curves that I mentioned, these holomorphic varieties, are minimizing. So what does this mean? We say that an integral current P is calibrated if there exists. So basically, you're asking for a closed volume form on this guy. So there exists a closed M form omega such that T, the mass of T is realized by integrating this M form against T. So T omega is the mass of T. You need this thing to have comass at most 1. And yeah, that's all you need. And yeah, the claim is, and it's really a one-line proof, which I always like to include, is that if T is calibrated, then it's minimizing. And we'll then see from this one-line computation to verify this, how to generalize this to this notion of being semi-calibrated, which is a bit more flexible. Okay, I promised you break in a minute, so let me write, in this case, the proof. So you take, right, you want to check that when you look at the mass, it's better than the mass of any competitor. You use the fact that this is T of omega, then you take an arbitrary homological competitor and you use the fact that this guy is closed to say that you have this, right? So this, right, when you dualize, it vanishes. Then you use the fact that this thing has comass at most 1 to say that this is the mass. Okay. And yeah, maybe we'll take a break for 5 minutes and then we'll see how to amend this in a local way to make sense of this being semi-calibrated. Okay. Right. So yeah, if our surface is calibrated with this calibrating form omega, then it's minimizing. And right, as I said, being minimizing and more specifically being calibrated is very rigid, and in general, yeah, it's not something we can always hope for. And yeah, I mean, for the purposes of when we're in some specific geometric setting where let's say we want to establish regularity for some kind of surface, maybe it's too much to hope for that it's really calibrated. And there's a more flexible notion of being semi-calibrated, which you can generalize being calibrated in the following way. So you basically, right, the rigid part of this whole condition is this part, the fact that it's closed. So let's say you drop this and you just ask that your M form is C1. And so then what happens to this computation and this? So maybe I do it in a different color so it's clearer. So I take this to be C1, and this is my definition of being semi-calibrated. And what changes in this computation is if you localize this to balls, then right, the thing you no longer have is, since this guy isn't closed anymore, this term won't vanish, but you can write this as this minus the extra term that you now have to keep track of. And the point is that this extra term is precisely this higher order error that I mentioned. So, right, so and I'm localizing all of this to a ball, small ball. And so then I get plus the mass of this guy, which so this is this is an m+1 dimensional integral current. So this, right, you can again dualize this to say that this is the omega, and this is localized to, right, we're localizing this to this ball. So in the end, I get that since this is m+1 dimensional and omega is now C1, we get this times, so we get some constant r to the m+1. So yeah, it's really something that's higher order. And yeah, this more general notion of being almost minimizing, as I mentioned, so being semi-calibrated in particular tells you that you're almost minimizing because you're minimizing up to this error term, which scales like something higher order relative to the scaling of the surface, which is like r to the m in balls of radius r. And then, yeah, right. What we've shown is that being semi-calibrated implies that you're almost minimizing. And so, okay, this I didn't want to erase because the point is that you can still, so you can still get an almost monotonicity for semi-calibrated objects, or actually more generally even for almost minimizing ones where, you know, but for general almost minimizers, the definition would be, so here, right, the general almost minimizers. I mean, there are different ways to define these. You can, yeah, I mean, sort of the weakest way you can define these guys is just by asking that here you have error r to the n plus alpha, that's some alpha positive. So yeah, this is precisely what we get here with alpha being 1. And what we have for almost minimizers is we have an almost monotonicity, which tells us that here we have an error term, which is C times r to the alpha, or for semi-calibrated things, we get r here. And yeah, as I said, so you can verify this by, yeah, the proof that works for minimizers by cone competitors. For general almost minimizers, for semi-calibrated ones, you can also verify this as you would do for stationary things by, right, just by testing the first variation formula with a radial vector field, because the point is that the first variation formula, I mean, it works more generally for currents that have sort of generalized bounded mean curvature, which you make sense of at the level of the first variation. And the point is that semi-calibrated surfaces, they're not just almost minimizing because the error takes this form. So maybe yeah, just raise the rest in a second, but the mark that semi-calibrated surfaces have generalized mean curvature, which is bounded uniformly, which you can check just by looking at what the first variation is doing. So this is precisely bounded by this guy. And this is because for these things, if you look at, you test this against a vector field, then this is T d omega. Okay, so this is what I was saying, that so the moral will be that all the regularity we can hope for and do get for minimizers, we can also get for these semi-calibrated surfaces. On the other hand, we can basically get nothing for general almost minimizers. So for general almost minimizers, and the main difference between the main strength of semi-calibrated surfaces relative to, right? So maybe the only time since I started doing research where I've drawn a Venn diagram is for the purpose of this. So just to clarify how these things relate to each other, you have area minimizers here, you have semi-calibrated surfaces here, and at the intersection, you have calibrated submanifolds. So somehow, yeah, the point is that you can hope in general for the same regularity for area minimizers and semi-calibrated surfaces, but in general, they don't necessarily relate to one another. They just, the thing that lies at their intersection is precisely the calibrated guys. Okay, and so, right, the moral will be that for area minimizers and semi-calibrated surfaces, we can get good partial regularity, but for general almost minimizers, so you can even consider, and almost minimizers were considered not at all. So almost minimizers were considered by Bombieri in the 80s, where he considered a slightly stronger notion of being almost minimizing than just having this kind of error. You can define being almost minimizing with an error of this type, with where you have this times r to the alpha. So it still scales like something higher order, but it's marginally stronger than this more general variant. And but in any case, so what Bombieri in 84 showed that for almost minimizers, he showed that the regular set, so this is, I mean, basically all we know in full generality also for stationary things, is that the regular set is dense. You basically get by Allard. And what we proved with my collaborator Max Gearing a couple of years ago is that Bombieri's result is essentially sharp for almost minimizers. So I think it was in 23, 24, 23. So we proved that there exist almost minimizers with full dimensional singular sets, in the sense that you can prescribe, so actually you can prescribe the singular set to contain any a compact subset K of, let's say, an M-plane with empty interior. And our construction is basically, you're prescribing, I mean, you fix this arbitrary set that you want your singular set to contain, and the idea is you want to put a branch point at every point in the set, maybe at more points. I mean, it doesn't matter, then it's even worse. But yeah, that's essentially what we do. So we can also make sure that, we have kind of two constructions. One works for, so these singularities that we prescribe, they're always branching singularities, because yeah, if you're like if you don't have, these are kind of the only ones you can hope to use to prove that you have like bad singular sets, because in the multiplicity one setting, you do have essentially the same regularity theory for almost minimizers. So it's really going to be at the level of branch points that you can build bad examples. And we have one construction that's kind of codimension one, where we build these branch points kind of in a fake way, where we construct our almost minimizers to be superpositions of C1 alpha graphs that meet tangentially on this bad set, basically. But then you can say, yeah, this is kind of a little bit artificial, because even though these are like flat singularities in the sense that you have a flat plane blow up at these points, you can still decouple into nice, smooth, well, C1 alpha surfaces. But we can do the same construction in higher codimension to really build like genuine branch singularities. So yeah, the situation for almost minimizers is pretty bad. On the other hand, the semi-calibrated ones, we still have essentially a reasonable underlying PDE from the first variation, and that's the gain that we get that allows us to hope for a good regularity theory. Okay, and before we start stratifying singular sets to get structural results, and then talk about more specifically these branch points, which are kind of the main enemy, maybe I'll just mention some examples of both calibrated and semi-calibrated surfaces. So one is coming back to the class of examples I mentioned before. So as I mentioned before, the holomorphic curves, or more generally holomorphic subvarieties, these are calibrated by the Kähler form. Which you can write very explicitly as, take a factor of half to make sure that it has comass at most one. So if omega and z are my complex variables, then it's this guy, one, which these are two, where, right, I'm taking 1 plus I omega 2 and z. And then you have also special Lagrangian submanifolds, which are half codimension in, say, Cn, or more generally Calabi-Yau manifolds. You have, and then, so these are both really calibrated examples, and then one example that's semi-calibrated but not calibrated, where they really exploit this kind of flexibility that I mentioned that you get from having a semi-calibration. These are, you get something like this from looking at spherical links of special Lagrangian cones. Okay, so these kind of objects that are calibrated and semi-calibrated arise naturally in many geometric contexts. And yeah, I mean, it's essentially, in general, the only way we know how to verify that some specific example is minimizing or almost minimizing in a suitably strong sense. I don't have time. Okay, so now let's start looking at the structural results. So okay, so as I mentioned, the starting point towards this is using this monotonicity or almost monotonicity that I mentioned. So we can use that to first stratify the singularities and sort of classically the so right, you can consider, so as I said, the monotonicity of mass ratios, it gives you tangent cones as blowups. A priori, these cones depend on the sequence of scales that you're looking at, and you can consider at points all possible tangent cones that you can get. So consider, so you look at the class at a given point of C, such that C is a tangent cone for T at X. Okay, so I'll probably stop mentioning this. So for T is always, until I say otherwise, T is always an area minimizing m-dimensional integral current. And then you can consider, you can define the case stratum T to be all the points in the support where, so the case stratum will be all the points where you have at most k dimensions of translational symmetry at the level of the tangent cone. So any in this class of tangent cones is translationally invariant, meaning you push forward under the translation map, and you get back the thing itself in at most k dimensions. Right, so the picture is you have, right, some cone C, which is a possible tangent cone, right? And it has some number, maybe 0, of like directions that you can split off, and like this thing that you, right, this, which you can check as a subspace, this sort of set of points which determine the directions in which you have translational invariance. This is called the spline. So here, right, this is the spine. And I'm saying that, right, for all points in the spine, if I take the translation map as defined by translating by this point, you get the cone itself. And so, right, so this is saying that at the level of any possible tangent cone, yeah, you have at most this number of dimensions of translational symmetry. And the sort of classical stratification result, which I believe is due to Almgren, but it's, is saying that you have a dimension estimate on the kth stratum, which is at most, so it's dimension at most k. So basically, this maximal number of translational symmetries is characterizing the size of that piece of the singular set. And it's also telling you that basically, right, the more translational symmetry you have, or rather, sort of conversely, the less translational symmetry you have, the sparser that piece of your singular set is. And sort of, yeah, this is one way to see why branch points are bad. So branch points, these are points, so I define these to be singular points with at least one flat tangent cone. And right, so this example that I wrote at the beginning, this branched example of this holomorphic curve w squared equals e cubed, right, that's a prototypical example of a branch point. And in fact, in that case, you have even a unique tangent cone that's a flat plane with multiplicity 2 at the origin, but you still have a singular point there. And right, the point is that this stratification tells you nothing at the level of a lower dimension estimate. But another way in which you can see that these points are bad is also at the level of Allard or de Giorgi regularity, because since you know you have at least one flat tangent cone, then at some sufficiently small scale around this point, your surface will be close to flat. It'll be close to some higher multiplicity plane, but you can't conclude any kind of regularity around this point. And right, what you need for de Giorgi or Allard in the setting of higher multiplicities is to know that you don't have a density drop. And that's exactly the thing that fails at branch points. So if you think about the w squared equals z cubed example, if you look at the density, then at the origin, the density is 2. But away from the origin, the density drops to 1. So, right, so also the problem branch points where failure of epsilon regularity so to apply Allard or Giorgi with higher multiplicity, you need the density to be close to some constant integer, basically q. You need e to k m to be, let's say, most q and q plus epsilon. Q locally. And this fails at branch points. Okay, so yeah, I guess what the plan is from now on is to, so right, already from this classical stratification result, which you can essentially prove by, so yeah, this classical version you can prove by like an iterative covering procedure, checking that you basically, at points in the kth stratum, things cluster around. So like, because any tangent cone has at most this number of directions of translation invariance, this tells you sort of where near the points in this kth stratum, other high density points are clustering, and they're necessarily clustering around sort of k-dimensional subspaces. And then you can use that to deduce this dimension estimate when you combine it with a covering procedure. And then basically a very quantitative version of that, which, so more recently, sort of towards saying more than just dimension estimates. And I think this was also mentioned yesterday. Neighbor Valtorta established rectifiability. I think this was in 2018 in this context. I mean, their original context was for harmonic maps into manifolds, but the observation is that if you have a monotonicity formula that, yeah, is behaving in a suitable way, so in this case, you're using monotonicity of mass ratios, you can repeat the techniques to establish that actually and I'll say a little bit more about the techniques behind this. Maybe, I mean, I'm supposed to finish in a minute, but maybe at the beginning of the next half of the lecture. So this is countably rectifiable, and this is using so-called rectifiable Reifenberg techniques. I mean, essentially, again, sort of, right, I mean, this is sort of a rectifiable parametrizations type result, right? So like an analogy to Reifenberg's topological disk theorem. Okay, so yeah, maybe I stop here for today, and then next time we'll discuss, yeah, sort of how to deal with branch points, and yeah, beginning with Armgren's big regularity theorem, and then also I'll mention more recent work of myself with Camilo de Lelis and Paul Minter, where we're able to strengthen this to rectifiability. And yeah, as you can see, the obstruction is really coming from these branch points, which a priori you just get that they're top dimensional, which is not, it's not gaining you anything. So you really have to work harder at those. And the tangent cones also tell you nothing because it's not distinguishing them from regular points of your surface. So you have to work harder there. Okay, thanks.
Thank you very much. Are there questions? So if not, I have at least two. At some point you said that semi-calibrated currents, they have a weak notion of mean curvature.
Yes.
So can you associate a varifold that it is compatible with the rectifiable structure of the current or not?
Wait, sorry, can you say?
So, since you have this weak notion of curvature square, can you also associate to the current a varifold structure that is compatible with this rectifiable structure of the boundary, or not?
Okay, I'm not sure. I think probably yes, but I'd have to think a bit more. Yeah, it's not immediate to me. Yeah, this I don't know. But I guess, yeah, I mean because so like somehow being semi-calibrated, like would your hope be to try and somehow generalize this to objects where you're not using the almost minimizing property, or like what would be? Yeah, I guess it's not clear to me how to like what would be the meaningful generalization of this to, yeah, because I guess at the level of just varifolds, yeah, I mean, you can sort of just directly work with conditions on the generalized mean curvature. So I'm not sure what one can gain from, yeah, I don't know whether it makes sense to consider. I don't know.
Okay. So are there a question? So if not, I have another one. So at some point you said that calibrated currents were like a subset of minimizing current. So is there possible to show an example of a global minimizer of area functional that is not calibrated? Because I don't understand exactly how do I show that the calibration does not exist.
So there are relatively recent works by Zhenhua Liu, who is a student, I think he's just graduated maybe, also of Camilo, where, so, right, he proved, so, right, so actually, okay, I don't know if there are like concrete examples, because he basically shows that in certain contexts you have that like non-calibratable surfaces are essentially generic.
The formats to have some.
So like they do exist, but I don't think there are like, it's not a constructive argument.
Because if I go very, very weak with definition of the calibration. Then...
Yeah. So I mean, they're highly non-generic in general, I think. These, calibrated submanifolds. But yeah, I'm not sure if there are like concrete examples, because the arguments of Zhenhua Liu are non-constructive as far as I'm aware. But yeah, he does essentially show that they exist, and there are many of them, at least under certain structures.
Okay, we continue with today's section. It's my pleasure to introduce Enrico Valdinoci from University of Western Australia. And his talk is about non-local minimal surfaces and phase coexistence model. Please.
Thanks, it's a great pleasure to be here. So I hope I will survive in spite of the jet lag. So let's see how it goes. If I fall asleep, please wake me up. And so I'd like to say something about non-local minimal surfaces and phase transition. So let me start to try to give some motivation for this non-local world. I was thinking, well, what the motivations could be. I thought, well, the first motivation is about our identity of mathematicians. So we are mathematicians, we do what we like. Well, sometimes not, we do what we can, but when we can, we do what we like. And so I think the non-local world is very nice, and so it's up to us to study if we enjoy it. The second motivation that I have in mind is about a surface tension. So surface tension is ubiquitous, because basically everything in life is about different features, and whenever you have different features, if they are relevant enough, you try to identify them, and you want to see how they are separated, right? So the easiest case of surface tension is that you have the water and you want to say that the interface minimizes area. But you wonder why this is so. Well, you may think that you yourself are an individual particle of water, or whatever substance you want, and you may think that particles are subject to intermolecular forces. So you may think that you are like an octopus with, well, octopus has 8 hands, but more than 8, n hands, and n pus, and you pull all your friends in the room, right? And why classical surface tension minimizes area? Well, it's because if you are in the middle of the room, you are pulled equally in all directions. But if you are in the front row, that is not so. So in the middle of the room, the forces average out. But in the first row, the only forces that average out are the left and right components, but the other ones are pulling you back. So you try to minimize this interface out of this average of forces. So this classical model, I think, is very good in two regimes, when you are in the first row and when you are in the middle of the room. But once you try to start to investigate what happens if you are in the second row, then the situation is a little bit more tricky, because you are in an intermediate state in which some forces average out, but some are still relevant. And this kind of arguments, so you may wonder, so who cares about the people in the second row? But the issue is that there are a number of situations, for instance, like thin films, in which many people happen to be in the second row. Okay, so it's not just a minority that you want to neglect and focus on the majority of the particles. There are a number of practical situations in which the second row, so the molecules that are at distance comparable with the molecular size, are not negligible. And so in principle, you want to study those phenomena as well. Now, if you put things like that, maybe it's too ambitious, because van der Waals forces are very complicated. So I will focus here mostly on toy models, if you like. So I will try to focus on some interactions that are designed in a way that you can study them mathematically with some analytical tools. But I would say that is not too bad, because even if the complexity of the real forces is very cumbersome, you may always think that locally you may zoom in, do your blow up if you want, and if you have the hope that the blow up represents something interesting, well, the forces nearby have to be somehow manageable and represented in a sort of scale-free way. Okay. So another motivation which is somehow related to surface tension is phase transitions. Well, we have already seen a number of seminars about phase transitions, so you know more or less what I have in mind. But again, if you want to consider phase transitions from a model point of view, you would like to say I have two phases, and I want to model the separation between these two phases. And your ansatz could be that you have some kind of potential formed by two wells, which favor the two pure phases. And then you have some kind of penalizations for unnecessary phases to pop up. So if you think like this, you may think that you have your domain, and you have a double well potential with two wells, with two minima in 1 and -1, and you have a domain, say omega, and you want to say that on this side you are +1, on this side you are -1, and you have a phase separation just because the potential W somehow makes the two pure phases, 1 and -1, energetically favorable. But strictly speaking, that cannot be the only reason, because if I keep splitting the domain between pure phases, well, the potential W itself does not prevent the formation of an arbitrary number of interface, which is somehow non-physical. So the reason for which we don't see so many changes of phases in nature is because there is a sort of ferromagnetic property that typically tries to align spins. So anytime you disalign phases, you pay a little bit of extra energy. And so in the classical theory, the idea is that you penalize the formation of extra interfaces by looking at an energy functional of this form. Well, I know people in Pisa would put epsilon here and 1 over epsilon there, but it's the same, right? I mean, the Pisan framework is more convenient because it would have finite energy when epsilon goes to 0. But if we are just speaking about minimization, this is maybe more intuitive to deal with. But my point is that the reason for which one puts here a gradient penalization is actually only phenomenological. One doesn't really know that there is a penalization of that type starting from prime principles. So again, if I consider that this penalization comes from particle interaction, it's not unreasonable to try to put, instead of a gradient term here, some kind of non-local object that takes into account all the possible particle interactions, may be weighted in such a way that the particles nearby have a stronger influence than the particles far away, but still that we try to comprise all these situations. Another motivation which is related to this is mathematical biology. In which again you may think that animals spread in the environment, and a natural situation, we will revisit this maybe later on, but just roughly speaking, a natural situation that you may think is that an animal spread in the environment because it's subject to a random walk. The animal doesn't really know the environment nearby and looks around wandering. But that's not really what happens in most of the cases, because even if the animal doesn't know the environment, some animals prefer not to wander around with a random walk, because that would not explore the environment sufficiently fast. So, for example, if you are a shark and you want to eat small fish, doesn't really make sense for you to look around like this, because fishes probably flee away before you eat them, right? So it's more convenient for a predator sometimes to have a fast drift in a precise direction and hunt there and repeat. It's like a hit and run strategy, right? And again, if you want to model this, it's more convenient to account for non-local operators rather than the classical Laplacian. There was another motivation I had in mind. Yes. Yes, the last motivation for me, well, so it's not the last. There is one more, which I think is the most important, but this will not be apparent now. So the most important for me will be a spiritual motivation in a sense. So the spiritual motivation is that the non-local world allows us to reconsider things that we knew, that we thought we knew. So before entering the non-local world, I had the prejudice that I knew something, very little, but something at least. Then I entered the non-local world and I realized that whatever I knew was either wrong or incomplete. So I think it's a nice change of perspective that allows for a development of knowledge based on new approaches, even to trivial things. But so the fifth one I had in mind is in a sense based on the stability don't take this word too technically, but the stability of the notion of perimeter. And this is already somehow related with the spiritual change of view, because what do I mean by this? So the notion of perimeter, so for me personally, my personal feelings when I hear the word perimeter changed during time. So when I was a kid, I've learned what a perimeter was, and I mean, you don't need to be a smart kid. It's obvious what a perimeter was, right? You take a square and you sum the size of the square. Great. So I thought it was a triviality. Then I came to Pisa, and you guys explained, the perimeter is a mess. Forget about it. You need Cacciopoli sets. But I was skeptical, right? Never trust Pisans. They're making things overly complicated. Yes, maybe they need to do that because they study very general objects. If you want to go for an existence theory, you need compactness, you have to enlarge your space, and you cannot rule out objects that are unpleasant. But maybe in real life, you don't need Cacciopoli sets. Now, the fact is that I think there is a deep reason for which the perimeter instead is a difficult object and requires sophisticated technology. And you don't need crazy examples to appreciate it. You just try to make this conceptual experiment in which you have to calculate the perimeter of a square. But nowadays we are lazy, we don't compute by hands, we ask a computer to do it. And so you have your computer, which has a grid of pixels. And each pixel has side epsilon. And you give your square to the computer, and the computer digitalizes it and computes the perimeter. And then the only thing is that, just to make things more interesting, your square is not aligned with the pixels, but it's rotated. And for instance, let me take a 45 degrees rotation because it's the easiest to calculate. I mean, the argument is general, but 45 degrees is easier to calculate. And suppose that the length of the side is 1. And now suppose that your computer does an approximation for which instead of the original square, any time that the pixel hits the square, counts it as a square itself. So the digital version of this, oh, this is not very visible. I don't know if the purple here is more visible. Basically, what I'm saying is that there are a number of pixels here that get counted in the cube, but they are just a numerical artifact. Okay. Now, visually, that's not too bad because remember, epsilon, you can make it very small if you buy a more expensive computer. But still the problem remains in the sense that the real perimeter, so suppose that this is the cube Q, the real perimeter of Q is 4. However, when you replace the diagonal in the pixel with 2 sides, so if I zoom in, the catch that I have epsilon here, so this would be the square root of 2 epsilon. But so you replace the square root of 2 epsilon with 2 epsilon. So you miss the right length by a factor of square root of 2. So the approximated perimeter of Q is 4 square root of 2. So the error is 4 times square root of 2 minus 1, which does not go to 0 with epsilon. Okay, and this is bad for applications because it's telling you that the classical perimeter is too rigid to be approximated in this way. So it would be desirable to have another version of perimeters which is instead more stable for this kind of approximations, and this would be good. So you would like something that resembles the perimeter. So it's not, of course, something out of the blue, but it's more stable for this kind of approximations. This would be good both for the theory and for the applications, because in the applications you may think, okay, let me compute something that is more stable and I have a good proxy for my desired quantity. But also for the development of theories, because sometimes when you get stuck trying to prove things in the classical setting, you have another avenue that is look for another approach, for instance, coming from the non-local world, that gives something that is more stable, more robust, and then maybe if you are lucky, you can pass to the limit or at least extract some extra information. So let me try, if you are convinced now that it's worth to explore a bit the non-local world, I will try to expose some techniques and ideas. And I think I won't be able to make a linear journey. So we're not really going from A to B. We try to have a direction, but then we will find some obstacles and we have to turn around and go back and forth. But so in principle, what I would like to consider is this notion of perimeter that was introduced by Caffarelli, Roquejoffre, and Savin. So the idea is the following. So you have a set E, and you want to reconsider what I was saying before. So you remember when I asked you to be molecules and pull your friends like a molecule? Well, the idea is that the set E will interact with the complement in the sense that any point X in E will interact with a point Y outside the set. So let us fix a kind of interaction between two sets. So if I have sets A and B in Rn, say disjoint, we can consider a kernel, an interaction kernel K, and consider the interaction between A and B to be just the integral over A, the integral over B, dx, dy, yes, so, k of x dy, k of xy dx dy. And then the perimeter associated to E is just the integral over E, the integral over E complement of k of xy dx dy. Okay. Now, similarly for the classical perimeter, in most of the cases, you don't really care about the perimeter itself, but you care about the perimeter in a given domain, because whenever you want to do minimization, you want to say, okay, I prescribe some datum and I want to minimize with respect to that datum. So if you have a domain omega, okay, and this, if you want, is Lk of E complement. If you want a domain, if you have a domain omega, then you have a set E. The definition of the relative perimeter of E in omega, something like this. You would say, okay, I consider the perimeter of E, but I remove all the interactions that do not have any point in omega. So this formally would be the perimeter of E minus the interaction of E outside omega and the complement of E outside omega. Okay? So with the idea that for me, whenever I will want to look for minimizers, I think that the set E is prescribed outside omega. So any contribution in the second part, in the negative part of this thing, doesn't really count. And I'm only allowing for perturbations inside omega. Okay, so my idea in the end will be that I say that a set I want to say that E is minimal for per k in omega, or k minimal in omega if its k perimeter is less than the k perimeter of F for every set F such that F outside omega coincides with E outside omega. Well, and strictly speaking, I will never say that a set is measurable, but I agree that to make sense of the integral, I have to restrict on measurable sets. But this is already an advantage, right? Because I don't need to restrict myself to Cacciopoli sets, for instance. So the level of technology at this stage is already simpler conceptually than the complexity required to deal with the classical perimeter. Okay, I need measurability because I'm making integrals, but that's it. Okay. Now, the only catch of this approach is that I have to go back and look at what I wrote here. Now, what I wrote here is not really convincing, because whenever I have something minus something else, the risk is that I'm subtracting infinity to infinity. So if I write things like this, strictly speaking, I may have plus infinity minus plus infinity, which is not determined. And it's actually what happens, right? But this happens even in the classical case, because if you want to compute the length of a curve, right? What is the length of a curve in omega? Would you really say that the length of the curve in omega, which is this part here, is the length of the full curve minus the length of the curve outside omega? Well, not really, because both the contributions are infinite. So you have to write it in a slightly nicer form, which is exactly the same as this, but making the simplification by hand. So let me relook at this definition. So if I have the perimeter, the K perimeter is the interaction of the set and its complement. And so I can write the interaction of the set and its complement, decomposing it into 4 parts. One, two, three, 4 part that now I'm going to write. And then I have to subtract and actually let me write instead of minus omega, intersect with omega complement. Okay, and so the interaction of E and E complement, I split it in 4 parts in the sense that I consider intersection in omega and omega, in omega and omega complement, omega complement and omega, omega complement and omega complement. So these 4 terms are exactly the first term, the K perimeter. But now the first and the last are the same, so I can simplify them. And so I can say, well, don't give this as definition, because this definition would not be well posed. Instead, consider this as a definition once you erase the last two terms. And so this will be my working definition for the K perimeter. Okay. Now all this is totally fine, but to make sense of some details of the theory, you want that your kernel K, well, there are several possible theories, okay? But so the one that I will discuss here is one in which the kernel K has some kind of regularizing effect. And so for this, you want the kernel to be somehow singular. This is also something that that happens in differential equations, right? So if you have a function and you convolve it with a nice kernel, doesn't really make your life easier. Well, it does in the sense that if you have a smooth kernel, you have a function, you convolve it. Any function convolved with a smooth kernel would be a smooth function. But then the equation involving this technique doesn't really have any smoothing effect. So suppose that K is smooth, then U star K is smooth. So if you have an equation like U convolved K equal F with F smooth, well, this doesn't imply that U is smooth, right? Because you have already convolved it with a nice kernel. So the moral of the story is that if you want a smoothing effect, for solutions of an equation, you better take K to be singular. Okay? Don't get me wrong, if you want a smoothing effect by the convolution, you better take K to be smooth. But if you want a smoothing effect on solutions, then it's better that K is singular. So I will look at singular kernels, and so I will focus on kernels such that are rotationally invariant, translationally invariant, homogeneous, and such that the K perimeter of the unit ball is finite. Exactly. Otherwise, that would be a problem, right? Now, if you do this, I think you don't have many options. Okay, let's first check that these are reasonable assumptions. Okay, they are somehow restrictive, and you can do things without these assumptions. But I think that these assumptions provide a general class of kernels, which is specific enough for us to do some calculations, but general enough to be interesting, right? So rotation and translational symmetry is something that many physical situations is totally acceptable. Homogeneity is tricky, I agree, but again, it's useful if you want to zoom in and out, because if you hope that your blow up or blow down is consistent, well, the kernel will have to respect some homogeneity. So you may think that maybe your original kernel was not, but the kernel that you use after a blow up will be homogeneous. So let's focus already on the case in which the kernel itself is homogeneous. And well, and the fact that the unit ball is fine, fine. But then the first three objects tell you that the kernel is of the form, well, some constant that I put it, well, let's say C, and then x minus y to some power. Now I like to write the power like n plus s, just because n is the ambient dimension. And now what happens is that if you want the kernel of the ball to be finite, the parameter s has to be between 0 and 1. And yes, so the reason being that you want this s to be positive, because whenever you take the interaction of the ball with its complement, S has to be positive because you are taking the interaction of this point with points far away. So when you compute the integral, you want that the tail of the integral has a power downstairs which is larger than n for integrability. So S has to be positive. But also nearby, you have near the boundary, you have interaction of particles nearby. And then if you compute what happens in the integral, you may think that you have just a hyperplane locally, right? So if you zoom in here, you have a situation like this in which you have the bottom of the domain interacting with the top of the domain, and you can do the calculation explicitly, and you see that S has to be lower than 1, otherwise you get infinity because of the singularity near the boundary, the proximity of the boundary. Okay, and if you want somehow to track the behavior of K with respect to the structural parameters n and s, you may think that this constant C actually depend on n and s, and a typical situation is to choose C and S of the form S 1 minus S. And the reason for this is something we may discuss later on more precisely. So from now on, I will mostly focus on this kernel, and I will use per S to denote the corresponding perimeter for this kernel and speak about S minimal sets when I'm minimizing the S perimeter. Okay, so couple of things that are useful is that the S perimeter as s goes to 1 recovers the classical perimeter. This is something we may discuss later on in further detail. And when s goes to 0, recovers, in a sense, the Lebesgue measure, some of the details that we will also discuss later on. But if you believe for the moment these two facts, then you can develop your intuition about what's going on. So you have an S perimeter, which is a non-local generalization of the perimeter for what it counts. But it's something that is accounting more for irregular sets. Because after all, if S is equal to 0, you have the Lebesgue measure, and the Lebesgue measure is not regularizing at all, okay? Measurable sets are finite Lebesgue measure by definition, right? So in a sense, you may think that the lower the S, the less regularizing the effect of the S perimeter is, with respect to minimizers, for instance. Now, one thing I promised at the beginning was that it was worth studying these objects because they were providing a more stable numerical approximation for the perimeter calculation. So let me convince you that this is in fact the case. So let's go back. Let's go back to this example here. So per S provides a more stable numerical approximation. So why is it so? Well, so the error between per S of Q and per S of Q epsilon. So let me call Q epsilon the approximated set, right? So this set here. So this set here for me will be Q epsilon. So the error here was the perimeter of Q minus the perimeter of Q epsilon, say in absolute value. And so here I consider instead the S perimeter of Q minus the S perimeter of Q epsilon. Now this error comes from these little pixels which are inside the set in one case or outside the set in the other. So whenever you compute the interaction, well, when I'm here in the region of Q outside the yellow pixels, the interaction of this point to this point to this point is not affected by the yellow pixels. So the error comes from the fact that some points in the yellow pixel interact with the exterior of Q, and some points interact with the interior of Q, but they are swapped around, right? So think that if I zoom in, so suppose that this was a pixel and you see it enlarged, so this is epsilon. So this point here in the original picture was interacting with this point here, because this is in Q and this is outside Q. But now if you replace it with Q epsilon, okay, and so also this point was interacting with this. But now if you place this in Q epsilon, this point is interacting with the complement. So the error comes from the fact that you are swapping the contributions inside the pixels. So the total error is bounded by the sum of all these yellow pixels on the boundary and the error in each yellow pixel is less than the S perimeter of the yellow pixel itself. Okay? Is this clear? Now, the number of yellow pixels, so the number of yellow pixels is like 1 over epsilon, because the size of the pixel is order epsilon, and I have to repeat it 1 over epsilon time to get the full length. And the S perimeter of each yellow pixel well, this is actually independent on the pixel itself. It's just the S perimeter of a cube of side epsilon. So this would be the S perimeter of what is 0 epsilon times 0 epsilon. Now, the advantage of working with things that are homogeneous is that we know how to compute these objects. So if you think about, you have a double integral with a kernel whose length of measurement is like meters to the power n plus s, and I have two Lebesgue integrals whose unit of measurements is meters to the 2n. So all in all, we know by scaling that this is epsilon to the 2n coming from the Lebesgue integrals minus n minus s, which is epsilon to the n minus s. But, okay, I'm in dimension 2 because my screen is two-dimensional. So this is actually epsilon to the 2 minus s. So all in all, this is like the number of yellow pixels times the S perimeter of each yellow pixel, which is always the same. So this is like 1 over epsilon, which is the number of yellow pixels, times epsilon to the 2 minus s, which happens to be epsilon to the 1 minus s. Now this makes me very happy because now the error is epsilon dependent and actually goes to 0 when epsilon goes to 0. So you see again how good it is that s is not equal to 1. because so this gives this nice stability, this nice stability property. And okay, so with this, I think it is worth studying studying the minimizers of the S perimeter, so these S minimal sets. Sometimes I will speak about S minimal surfaces, think that the boundary of this set is a surface, but I may also think that the set itself is an S minimal surface. This is something that in the literature happens a lot, that you think that the set itself is a surface, but strictly speaking, the surface is the boundary of the set. Okay, and the first question, usually when you have a variational problem, is try to understand the Euler-Lagrange equation. Okay, that is just the first variation of the function. So you would like to say that a necessary condition for a set to be a minimizer is that it satisfies a nice equation. And if you think about the classical case, this is of paramount importance. Actually, I think the Euler-Lagrange equation of the perimeter is the mean curvature equation. So a set, if a set minimizes the perimeter, then it has the boundary has zero mean curvature. Okay, assuming that everything is smooth. And this historically changed mathematics, because if I'm not mistaken, the mean curvature equation is the first PDE ever written by Lagrange, I think, exactly studying the minimization of surface. Well, maybe people wrote a PDE before, right? But not consciously, right? That is the first case in which a PDE is written in a modern terminology with a modern mind. So I find it very curious, because I would have supposed that Laplace of u equal to 0 came first, but apparently mean curvature equal to 0 came first. And that was important because minimizing a functional is difficult to, at least for me, it's difficult to visualize, right? You have many competitors, and in principle, you have to fight with all possible competitors. But the mean curvature equation is something geometric, and so you may try to visualize the fact that the curvatures are compensating themselves. So our goal would be now to try to get a nice equation for the S perimeter, and try to visualize how this helps in practice. And then we bump immediately in the sixth motivation I was telling you at the beginning, right? The spiritual motivation that this will turn our understanding of the classical world, in a sense, because we will have to revisit what we know about the mean curvature equation to discover that there were hidden things that probably we didn't notice at the first glance. So first of all, how to obtain the Euler-Lagrange equation. Okay, so on many occasions, I will propose a wrong proof, but I will tell you where I cheat, okay? Because the real proofs are much harder, but in a sense, we lose the intuition, how you guess the right result, right? So the Euler-Lagrange equation was first established in the Café-Joffre Samin paper, and the proof is very hard. Well, they don't really tell you how they guessed it was true before doing the construction. But I think that the guess is this. So suppose that you want to minimize the perimeter, right? And one convenient thing to do is, well, take a general kernel K. Well, suppose even that it's a form K of x minus y, if you want. That's not really relevant, or at least that it's symmetric in x and y, or it depends only on the distance between x and y. Now, it's convenient to think that this is actually half of a semi-norm. So I'm using the notation that the characteristic function of E is just 1 if x is in E and 0 otherwise. Okay, and okay, this is obvious, right? Because if both x and y are in E, this is 0. If both x and y are in the complement, this is 0. So the only possibility is that x is in E and y is in the complement, in which this case is 1, or vice versa. So I have 1 plus 1 and 2 to divide. So this is just an algebraic observation. Okay, so this is a useful observation if you like functional analysis. So let me write this on a side, because I'm not really using this here now, but when k is actually 1 over x minus y to the power n plus 2s, the right-hand side is like the Gagliardo semi-norm square of the characteristic function of E. So you can relate this object to fractional Sobolev spaces. I'm not really using this here now, but it's good to keep it in mind. Now, what I will do, I will take derivative of this object. So if this were a semi-norm, formally when I differentiate it, I would get, so the first variation if one has to guess, would be the integral over Rn of k e x minus k e y kappa of x minus y dy equal to 0. Okay, that would be the natural guess if you differentiate a semi-norm. Strictly speaking, you cannot do that for at least a couple of reasons. So, first of all, this is not any function, right? If this was you differentiate and you get that. But this is a characteristic function, so you have to take variations not of u plus epsilon phi, but of e plus epsilon something, so that the variation is inside the characteristic function. So you're not really allowed to be so brutal. The second thing that is somehow problematic is that in my case, kappa is singular, k is singular. So this goes on the denominator, so this is actually even more singular. So there are a couple of things that you have to adjust doing this. So this is not the first variation, as we may suspect, but it's close enough to the first variation. So the actual first variation is like this. So you have a point x on the boundary of E, and you have a structure which is very similar to what I wrote with a couple of caveats. So you take the characteristic function of y minus the characteristic function of the complement of y divided by the kernel, x minus y to the n plus s dy equal to 0. Okay, so this is almost the structure that I was proposing before, with a couple of caveats. So you're not using the characteristic function itself, but you're using this sort of scale characteristic function, so the characteristic function of E minus the characteristic function of the complement. This comes from the fact that you are not taking perturbation of the characteristic function adding a smooth function, but you are modifying the set itself. The second caveat is that this object is very singular. So now you have a point at the boundary, and the fact that the point is at the boundary is natural because you are taking variation of the set, so it's natural that the equation sits on the boundary. But the integrand itself is not integrable according to Lebesgue, because if you put the absolute value, you risk to integrate 1 of x to the x minus y to the n plus s. So you have to take this in the sense of principal value. So for me, the principal value sense is simply that you are taking the limit as epsilon goes to 0, the integral of Rn minus b epsilon of the singularity of the function. And now this is much better, because here you see already that one of the main ingredients to study non-local objects is to spot simplifications. Why this principal value is useful in this case is because suppose that E is a nice surface, and then this is the ball of radius epsilon. Okay, this is x. This is the ball of radius epsilon at x. Then, if it's a nice surface, you may think that near here I have a paraboloid touching from the top, the paraboloid touching from the bottom, and then this quantity becomes finite because so this numerator here, let me give a name for short, so I will call this key tilde of E. Key tilde of E is like the characteristic function of E, but it's not 0, 1, it's minus 1, 1. And actually, let me change my mind. I know that 0 is equal to 0, but I prefer to write it with the complement here, for a reason that we will see in a second. So I write key tilde as something that is minus 1 in the set and 1 outside. I think this is more convenient for something I will say in a second. Okay, but no matter what, so if this is the set E, chi tilde is 1 outside E minus 1 in E. So I may not know how E looks like, but if E is smooth, below this parabola is minus 1. Above this parabola is 1. So since I'm allowed to cancel these contributions, the only object that contributes to this integral here is the part of the set which is trapped between two parabolas. And that is what makes this integral convergent. Because it's true that you have a power here which is extremely dangerous, right? Because to me, already 1 over x to the n is dangerous when I integrate locally. So x to the n plus s is super dangerous. So I need to beat this power by 2 extra powers, because, or at least more than 1 plus s, because I have to beat s and something more. But so I get these extra powers exactly because I have a quadratic trap from these two parabola. So the bottom line is that this object is well defined on smooth sets thanks to cancellations. Now, why am I cheating here? The fact is that you have to reconstruct this argument. If you want to make a rigorous proof, now you have to change the order of the pieces of the puzzle. Because to make their proof work, what Caffarelli, Roggioffre, and Savi need is to introduce the notion of viscosity solutions for these objects. Viscosity solutions mean that you can touch your surface from one side with a ball. Now, you may complain that here I'm touching from two sides. But I tell you, well, if you touch from one side, you get that this object is not finite, maybe, but it's only plus or minus infinity. So you have only one direction of divergence. So it would still be well defined in the limit. Maybe the limit is plus infinity, or maybe the limit is minus infinity, but the limit exists. So this idea that you look at points that are touched from one side by a ball somehow is useful because it hides this kind of trapping property here. And how do you look for variations? I was saying at the beginning, oh, you have to look for a set, and then you have to look at appropriate variations. Well, if you touch with a ball, roughly speaking, suppose that you're touching from this side with a ball, you can take a slightly larger ball and then look at this object here as your competitor. So you can have a class of competitors for which you can estimate carefully the errors of the interfaces and do your calculation. And when you do so, you exactly get this object here. Now, if you're still wondering why I decided to take the complement instead of the other way around, is because I want to say that this object here is the S-mean curvature. And I call it HSX. And I would like to say that the S-mean curvature of the ball is positive, for instance. Now, if you have a ball well, the ball is rotationally symmetric, so the HS mean curvature is constant, but I would like it to be a positive constant because the ball is convex. And now, so suppose I compute it here, for instance. I can take a symmetric ball. Now, with my notation, the key tilde is equal to -1 in the set and 1 outside. So especially 1 here and 1 here, 1 here. Now with the little game of symmetry, this contribution here and this contribution here cancel. So HS of the ball is positive. Fact, it's a general property that HS converges to the classical mean curvature. Well, up to constants, because here I'm, yes, in principle here, if I want to be careful, I have to remember that the kernel was not x minus y to the n plus s, but there was this constant here that was renormalizing things. But so basically, the S mean curvature equation is approaching the classical mean curvature equation. This is basically the thing that matters. Now, if I still have 5 minutes, I want to give you another example of the spiritual change when you enter the non-local world. So, yes, when I was a student, they told me, for instance, the Laplacian is the sum of the second derivatives. Okay, so I take derivatives in all the coordinate axes. But then they told me, oh, but the Laplacian is invariant under rotation. And I thought, it cannot be because the axes are not invariant under rotation. You tell me what is the first derivative, you tell me what is the second derivative. That has nothing to do with an oblique derivative, right? So there is something wrong. But then they told me, no, just do the computation. And you find this amusing fact that the Laplacian is invariant under rotation, even if it doesn't look so at a first glance. Now, there is another option. Rather than defining the Laplacian as the sum of the second derivatives, another thing that you can do is to say that the Laplacian of u is, well, you take u of x plus y minus u of x. So you integrate in a small ball near x. Well, you take the average and you divide, I think, by 1 over r square, and you take the limit as r goes to 0. Well, up to a constant, you compute because you expand u at the second order with the Taylor expansion. The gradient of u times y will average out to 0 by symmetry. So you have a second order, but of this second order, only the pure derivatives survive, and you get the Laplacian, okay? But the reason for which I think this is a much more natural definition of the Laplacian is that here you see immediately the rotational invariance of the operator, because the ball is rotational invariant by definition, okay? So this is a definition that immediately says that it doesn't really matter that you compute derivatives according to the Cartesian frame, and every other orthogonal frame would give you the same result. Why I think this is relevant for mean curvatures? Well, because the same happened with the mean curvature, right? They tell you to compute the mean curvature, you have to take the curvatures in an orthogonal frame on the tangent plane, right? And again, it's not obvious to me that if you take curvatures in that direction or curvatures in that direction, the average is the same. And it's not obvious to me that you can recognize that the curvature of the sphere has a sign just because the sphere occupies less space than all the space available, okay, which is what you use here. But there is a similar thing that you can do for the classical curvature. So if you have the mean curvature, so you have a set, okay, and you want to compute the mean curvature, one way is to look at this chi tilde of E in a ball of radius r, and now divide, I think, by 1 over r, and send r to 0. Okay, I don't know if you have ever seen this formula for the mean curvature. I mean, it's a triviality, so I'm not saying that this is anything ingenious at all. If you want to check it, I'm not a geometer, so if I can quote Camillo once said, I'm a bloody analyst, so if I want to check this, I just put coordinates on the surface, I compute it, and I get, so I put coordinates, of course, taking coordinates with respect to a horizontal tangent plane, and I do that calculation, and what I get is the Laplacian of the coordinates with respect to the horizontal tangent plane, which is exactly the mean curvature. So if you just write coordinates, it's a triviality, but it tells us several things, because it tells us that, again, if I want to understand the classical mean curvature, the classical mean curvature has the same properties as the ones that I use here. There are hidden cancellations, even for the classical mean curvature, that help to understand the sign of the mean curvature based on the shape of the set. Well, the classical mean curvature is local because everything is infinitesimal, but it has the same type of structure. So if I look at this version here or this version here, I would say, well, it's pretty much the same because I'm considering the chi tilde. I'm dividing by a kernel. Well, here the kernel is a distance to the power n plus s. Here, it's basically n plus 1, if you want, right? But because this counts as 1. But it has the same kind of structure, with the only difference that here, the kernel is very localized at the point, and here the kernel is diffused in space. But in a sense, often the game will try to understand what the fractional mean curvature is based on this kind of geometric approaches and cancellations which reveal additional simplifications. And with this, I think my time is over. I also forgot to do the break, so sorry.
Thank you, Enrico, for your lecture. Are there questions?
Yeah, just a curiosity. When you define the perimeter of E in omega, why don't you consider just the first term, the interaction between E inside omega and the complement, just to avoid a boundary of E which coincides with the part of the boundary of omega? Or no?
Yes, that's a good question. Okay, so you want to look at only the interactions in omega. So you want to say, I look at the interaction between E intersect omega, E intersect omega complement.
E
Sorry,
yeah.
E complement. Yes.
Yeah.
E complement in omega, right?
Yeah.
Yes, you can do this, but my feeling is that if you do that, the minimizer would just be either the empty set or omega, because then you get zero. So
because you have an extra boundary which coincides with the boundary of omega.
yes, exactly. So this is also, I think, something that required me a change of mentality with respect to the classical case. So in the classical case, one speaks about the perimeter of a set in a ball. Now, people sloppy like me never checked whether the ball was open or closed. But strictly speaking, you have to take it closed, because otherwise you would get the empty set or the ball itself. And the fact is that in the classical case, basically you have this theory of trace that tells you that you prescribe the set E along the boundary of the ball, and this gives you a reasonable definition of perimeter inside the closed ball. Now, when you do this in the non-local world, unfortunately, sets of measures zero don't count. Another thing that I didn't say explicitly is that for me sets are equivalence classes, because I will integrate them anyway, right? So when I say that the set is S minimal, well, I'm saying that a representative of that is S minimal. So when I will say that an S minimal set does something, I mean there is a representative of it doing so. But in terms of minimization, this means that I cannot just prescribe the trace of the set. I need to prescribe an exterior datum. But this, okay, if we have time, we can discuss more tomorrow, I think. There's a very nice practical implication. So, for instance, when you speak about mathematical biology, you can use these ideas to speak about a biological niche. So what is a biological niche? Is an object in which the animal lives sufficiently comfortably. If it goes outside, well, the external environment is not lethal, but it's adverse enough to let the animal return to the original niche. So this idea that you have to prescribe the complement of the set rather than the trace is something useful if you want to use these ideas, for instance, in mathematical biology. So it's not just a matter of measure theory, it's a matter of life, in a sense.
Other question? Okay, if not, we thank Enrico again.
Thank you.
Okay, so welcome everybody to this afternoon session. The first speaker of this afternoon is Serena Dipierro from the University of Western Australia, and she will speak about the strict maximum principle for non-local minimal surfaces. Please, you can.
Thank you very much. So first of all, I would like to thank the organizers for inviting me to this conference. It's a great pleasure to be here in this conference with very young speakers and also organizers. So I will talk about a result from last year, obtaining collaboration with Ovidio Savin and Enrico. And this is about like a very classical problem, a very classical question, which is related to essentially maximum principles. So the question is simple. So essentially, can we have minimal surfaces, one included in the other? Okay, so let me state it in a more, I don't know, maybe mathematical way. So suppose that we are given two sets, E1 and E2, in a Rn, and suppose that they minimize some kind of perimeter functional, for instance, the classical perimeter, or the non-local perimeter, which is the one that we saw this morning with Enrico, and I will recall later on. So in a given ball, okay? So so they minimize the perimeter, this perimeter function in, say, some set, say B1. And we suppose that E1 is contained in E2, but that they touch at some point, say the origin. And then can I say that they actually coincide? Okay, so is this true? Can I have some kind of strict maximum principle? And if this is true, and we may believe it is true, it's a reasonable proposition, is it obvious? Is it easy to do it? That's the thing. Okay, so let's try to look at a very simple option that we have here. So for instance, let's look at the classical case. So classical minima surfaces. So basically, so we have these two sets, they touch at the origin. So suppose that we can write them as a graph near the origin, near the touching point. So at this point now we have two functions, say u1 and u2. They satisfy this inequality, so because the sets were one included into the other, and they are equal at the origin where they touch. Now, they are both solutions of a nice quasi-linear equation. Okay, so the mean curvature equation written for graphs, for which one way or another I can have a maximum principle. And so by strict maximum principle, I can say that actually the two functions must coincide. Done. Okay, so let's try to reproduce this scheme for the non-local minima surfaces. So for the moment, just let's suppose that we know what they are. Actually, we know because Enrico told us this morning. So we do essentially the same thing. So we have these two sets, and we have a non-local mean curvature equation that reads like this. So for me, chi tilde of Ej is essentially, so this chi tilde is exactly what Enrico wrote this morning. So chi tilde of a set E is, say, the characteristic function of the complement minus the characteristic function of the set. This is exactly what Enrico had this morning. Oops. And so this is one, okay, if the point belongs to the complement of the set, and it's -1 if it belongs to the set. And so we have this mean curvature equation for both sets. Okay, so we write it for both sets, and we take the difference, and if we take the difference, we have exactly this integral of the chi tilde for E1 minus the chi tilde for E2. And now it's even simpler than maximum principle. It's really just set inclusion here, because the integrand is non-negative, because one set is included in the other. So if E1 is included in E2, the complement of E1 includes the complement of E2. So somehow we have a sign for the numerator in the integrand. And so this is just set inclusion. Okay, so even simpler than looking at maximum principle for a complicated equation. And so because this has to be 0, this must vanish, which means that basically one must coincide with E2. And we are done again. Okay, so what is the problem? So if we were really done, we could finish the talk now after 5 minutes. The problem is that we are relying on the fact that we can write an equation. So we wrote an equation in both cases for the two sets at a specific point. And in one way or another, we were applying some kind of maximum principle to that equation. Okay, so what if we cannot write such an equation at that point? Because, well, we know that minima surfaces and also non-local minima surfaces could have singularities. Okay, in higher dimension, they can have singularities. So maybe at that point, the touching point, we cannot write the equation. So if the touching occurs precisely at one of the singular points, we cannot really write the equation. And so we cannot really do this one slide argument. So we have to find a way to overcome this issue. Okay. Okay, so a very beautiful proof of the strict maximum principle in the classical case of classical minima surfaces is contained in this paper by Leon Simon. It's a kind of an old paper. And basically, so he proves a strict maximum principle using essentially blow up and some nice geometric Harnack inequality. So I will try to somehow summarize, so give some, like, what I think are the main steps of the Leon-Simons proof, and then we will see how we can redo what Leon-Simons did in the classical case in the non-local setting. Okay, so the proof goes like this, more or less. So it will be, of course, a sketch of the proof with many details that I will really sweep under the rug. So we suppose by contradiction that the two sets do not coincide. Okay, so E1 is not equal to E2. So the first step is, okay, I want to reduce to the case in which E1 and E2 have the same tangent cone at the origin. So they somehow touch at the origin. Okay, so that's the point. And we can assume it's singular because otherwise we can do the one slide proof. So I want to reduce to this case because if not, so if they don't have the same tangent cone at the origin, I can blow up, I can take a blow up at the origin to obtain two different minimal cones. Okay, so I can do that because there is motonicity formula. So I know that if I take the blow up, I end up with minimal cones, one included in the other, okay? And they are different, okay? Because otherwise we would have stopped in the beginning. So this is the situation. Now I'll try to make a picture. The picture will be, in the best case, three-dimensional. Let's see, so I have these two sets. Maybe they touch at the origin. Whatever, something like this. So one is included in the other, then I do a blow up. And I end up with cones, say this one and this other one here. And this one is maybe, I don't know, something like this. Okay, so now I have my two cones, they do not coincide. So what I do, so the cones, I call them E prime 1 and E prime 2. Now I rotate E prime 1, so this is going to be E prime 1. And this is E prime 2. And now I rotate E prime 1 till, okay, in this picture they touch along a line. So let's see if I can make this work. So this is E prime 2. Okay, and now I rotate E prime 1 till they touch here. Okay, now I look at points along this line. So I blow up again, say, at a point along this line. I do a blow up. And now if the tangent cones are the same, okay, I replace basically my original set with these new sets. And I look at this situation. And I go to step 2. If not, I do a dimensional reduction. Okay, so now I look, let's say now I was three-dimensional. Now I look at the two-dimensional section here. So I just look at the two-dimensional picture, and I do essentially the same thing. Okay, so I have, so because I have a good theory of dimensional reduction, I can say that I obtain minimal cones in one dimension less, one containing the other, and then I keep going. Okay, so if they do not coincide, I take the rotation, I do the blow up, and I check if the cones coincide. Okay, so essentially by this repetition of blow ups and dimensional reduction, sooner or later I will have to stop because in low dimension there is one and only one minimal cone because we have regularity. So at some point that's the only one that I can have. So at some point I have to stop. Eventually in dimension 1. Okay, we don't even need like very fine regularity theory. So at some point I can stop and I can look at a replacement of E1 and E2 with these, I don't know, E2, E3, E whatever sets, okay? Okay, so this is the step 1. So the step 1 needs a good theory of, okay, blow-ups. So I need to be able to take blow-up. So I need the monotonicity formula. I need to be able to take blow-ups and obtain minimal cons. And I need a good theory of dimensional reduction. This is what we need from this step. Okay, so once I have that, now I want to write an equation away from singular points. Okay, so this is the second step. So what I do, first of all, I kind of localize my problem. So now I take a larger ball, say B capital R, and then I cover the singular points with a family of very small balls. Okay, and I know I can do this because the singular set I know is small. So I can always cover with a nice family of small balls. So now I am localizing the problem, taking a big ball, and I am removing balls where the singular points are. Okay, and now, okay, I replace E1 and E2 with the blow-up sequence. So I do the blow-up. And I know now they have the same tangent cone. So let me do another picture here. So here I have my limit cone, say this one. And then rather than looking at E1 and E2, I'm going to look at, say, E1K, E2K for K sufficiently large, which are essentially blow-up sequences for E1 and E2. And if K is sufficiently large, they are both very close to the limit cone. So maybe, I don't know, they do something like this. So this is going to be E1, and this is going to be E2, okay? Something like this. And yeah, I have localized my problem. So I'm looking at, I don't know, whatever happens inside some ball B capital R. And I am removing, I don't know, singularities from the tangent cone. Okay, and now I know that outside of these small balls, these sheets that I'm looking at are smooth. And so what I will do, I will take W. W is actually a WK, which is essentially the distance between these two sheets. Okay, say in the normal direction with respect to E1. Okay, so I'm looking at E1 here. And W is, I don't know, I take the normal. W is the distance between these two sheets. And then what Leon Simon did, he checked that W satisfies a nice geometric equation, essentially led by this operator here. So this is the Laplace-Beltrame, okay, on the sheet, or along the, say, E1. And then I have the square norm of the second fundamental form. Okay, so this takes care of the curvatures here. So the main part is going to be the Laplace-Beltrame here, because the good thing is that this part of the operator will have a sign. So one way or another, we will throw it away somehow. And then, of course, there are other terms, but they are not very important. I mean, they are under control. And once we take the limit in K, they will go to 0, essentially. So this is the leading part of the equation. Okay, one thing that one should notice is that W is bigger or equal than 0, because the sets were one included in the other. And in fact, I can say that they are strictly positive. It is strictly positive by the strict maximum principle, because if they touch at some point, once I have removed the singular part, if they touch at a regular point, I can do the one-slide proof and use the maximum principle. So in fact, I can say that W is strictly positive, okay, everywhere. So now I pick a point, X star, and I normalize W at this point, okay? That is, I look at this function V, which is W divided by W at X star, okay? So this was essentially the second step. The second step is I need an equation, some sort of geometric equation. Okay, and once we have done this, I want to pass to the limit. So I need some kind of regularity theory, essentially, for this equation, which one can do. So one can find for this equation. So one can bound W, sorry, this is V now. So Vk uniformly in K, you can pass to the limit. And once you pass to the limit, the term with the second fundamental form here is non-negative. And so what we obtain is a simple equation like this. Okay, so this is the Laplace-Beltrami of infinity smaller or equal than 0. Now, and only now, I will invade the space. So I will send this capital R to plus infinity, and I will shrink the covering of the singular set. Okay, so I will take the radius of these small balls to 0. And in this way, I have an equation that is satisfied in some distributional sense at all regular points of my sheet that I will call Matkalar. Okay. Okay, so here the step 3 is essentially we need a good regularity theory for this equation, and we need to be able to pass to the limit. Okay, and then step 4, bless you. Step 4 is Harnack inequalities, geometric Harnack inequality that was proved for classical minimal surfaces by Bombieri and Giusti, and says that basically the infimum of this V infinity is bigger or equal than the integral of infinity, and this is strictly positive because I renormalized V. So V was the renormalization, the pointwise renormalization of W. Okay, so it is 1 at some point, and this is preserved in the limit. So it is pinched at some point. And that's why we needed to do this renormalization, because this now guarantees that this integral is positive, strictly positive. Okay, and now if this is bigger than 0 for large K, then Vk is bigger or equal, say, than M over 2. But this means that if we go back to Wk divided by Wk at x star is bigger or equal than N minus 2. And now there is another subtle information that we need, which is sublinearity at the origin. So these two sheets share the same tangent cone, which means that the Wk must be sublinear at the origin. Okay, which means essentially this, that for every small theta, if I take the supremum of Wk in the regular set intersected these annulus b2 theta minus b theta, this is bounded by a constant times the supremum in this b3 over 4 minus b3 over 8, but multiplied by theta. Okay, so this comes from the fact that they have to have the same tangent cone. If this were not true, they wouldn't. Okay, so now there is a bit of a technicality here that I will not discuss much, but the thing is, if you want to use this, you need a good notion of regular. Okay, you need the notion of good regular points, because the problem here is that. So essentially, what we are trying to do, we are trying to maximize Wk divided by the norm of x. We want to maximize that, and the problem is this supreme. I mean, this maximum can degenerate, can go to the singular part. Okay, but we need this point somehow to be on the regular part, because that's where we have the equation and we can do whatever we want to do. So we need somehow to select good regular points whose distance to the singular set is comparable to their distance to the origin. So this is a bit of a technicality from geometric measure theory, but I mean, it can be done. Okay, and now that we have that, we take a compact subset of the regular set in this annulus b2 theta minus b theta, non-empty. And so, okay, we have this chain of inequalities. So M over 2 is smaller or equal than the infimum of Vk, so of Wk divided by Vk x star. And then I take Vk x star outside, and this is simply smaller than the supremum over all the set here. And now I use the sublinearity. So I take a theta outside, and then I have the supremum over a different set here. And now I use, this is just the classical harmonic. And now everything is bounded, and then I have theta here. And so if I take theta sufficiently small, I get a contradiction. And this is done. And so essentially the step 4 is, so relies on the existence of some kind of geometric Harnack inequality of this type, the Bombieri-Giussi Harnack inequality, which we are going to need in our setting. Okay, and so in the next part of this talk, I want to discuss about the non-local setting. Okay, so the non-local setting, I'm going to surf over this a bit because Enrico already talked this morning. So yeah, the surface tension is replaced now by, is now the byproduct of long-range interactions, and there are many new things that happen in this setting that, I don't know, maybe Enrico will talk about tomorrow. Let's see. But I'm going to skip for this talk. And so the non-local perimeter is defined using this interaction. So this interaction is a double integral over A times B of this nice kernel with S in between 0 and 1. This is defined for any couple of disjoint subsets A and B over N. And then the non-local perimeter is the interaction of the set with its complement, and I'm using essentially the second, let's say the definitive definition that Enrico gave, which is the one that has the 3 terms, where we count all the possible interactions between the set and the complement, like this in this picture. So I have E in omega against the complement of E in omega, E in omega with the complement of E outside omega, and E outside omega with the complement of E in omega. And I don't consider the interaction outside, because that is infinite essentially. Okay, so they were introduced by Caffarelli, Roch-Joffre, and Savin, and they gave, okay, so they basically laid the foundation of the theory. So they have an existence theory. So given an exterior datum, their existence as minimizer. We have some sort of maybe comparison principle. So this says that if I have a set that minimizes the perimeter in omega, and outside omega, the boundary of the set is contained in a given slab, then the boundary of E has to be contained in the slab, also inside. And this says essentially that the hyperplane is a minimizer, okay? Because it's the only one that is contained in any slab, but whose boundary is contained in any slab. There is an initial statement about regularity theory. So if you have a minimizer in B1, then the boundary of E is C1 alpha, say inside in B1 half, outside a closed set sigma whose Hausdorff dimension is less than or equal to n minus 2. Okay, so first of all, one can go here from C1 alpha to C infinity, because there is a paper by Begonia Barrios, Alessio Figali, and Enrico, where they essentially do a bootstrap argument to go from C1 alpha to C infinity. So one can in principle replace C infinity here to C1 alpha. And the second thing is that, okay, this is a good regularity result, not very good for our purposes, and I will tell you why. Because this one, so we can still have like point singularities in R2. So not even R2, we cannot even like have a full regularity statement in dimension 2, according to this result. And then the other thing, okay, we have an equation. So if I take a point that sits on the boundary of E, we have the non-local mean curvature equation that Enrico discussed like thoroughly this morning, and we also wrote in the slide before. So we have essentially this equation, and this is the one that we are going to use. Okay, so we have some very good news for the moment. So we have a good theory of blow-up. So there is a monotonicity formula, so we can do blow-ups. We can say that we can obtain minimizing cones. We have dimensional reduction. So essentially, this part takes care of step one. So we can do step one. We can reduce to the case of sheets with the same tangent cone. So that is good. Some more good news is that the n-2 in this statement here can be actually improved to n-3 because in dimension 2 we have a regularity result. Okay, so this was done some years ago now by Ovidio and Enrico. And it says essentially that, non-local minimal surfaces are smooth in dimension 2. Okay, so the only minimal cone is the trivial one, the hyperplane. And so this allows us to find a nice cover of the singular sets. So the singular set is sufficiently small, so this is good. And it will allow us also to do some capacity argument later on. Maybe I will mention it later on. But this is very important. Like without this, we wouldn't be able to like carry over the proof till the end. Okay, so let me try to, I don't know if Enrico is gonna give you the full proof of this. I don't know. In any case, I will try to give you an idea why this is true. For at least a couple of reasons. One is that it is one of my favorite, at least in the setting of non-local minimal surfaces. I think it's beautiful. It's maybe not super demanding from the technical point of view, but it relies on a brilliant idea, I think. So one really needs like to find the right thing, and that's what I want to tell you about. And the second reason is because it will also tell us somehow how the non-local setting is different from the classical setting, and why somehow we need maybe some new ideas to deal with the regularity theory in the non-local setting. So this is pretty much what is known in the case of non-local minimal surfaces in terms of regularity theory. So dimension 2, essentially. There are no counterexamples in higher dimension. This is pretty much really what is known. So it's a kind of a difficult problem. Okay, so this is basically the idea. So what do you want to do? You want to rule out essentially corners. So maybe you look at the simple one. Of course, then when you do the proof, you have to rule out every corner. But let me stick to the simple case of the first quadrant just to give you this idea. Okay, so what would you do in the classical case to rule out the corner? Okay, you simply cut here. This line here will be shorter than the corner, so this cannot be a minimizer. So you find a better competitor. If you do this, if you just take the line here in the non-local setting, okay, you have to compare now the non-local perimeter of the corner with the non-local perimeter of the line. And if you write down all possible interaction, it's not clear that one is smaller than the other. Okay, so they are difficult to compare. So that competitor, for some reason, it's not that it doesn't work. We are not able to say, oh, look, this energy is smaller than this other one. So clearly that competitor is better. So the idea is, let's find a different competitor, a better one for the non-local setting. And let me do the proof in the classical case. So let me give you a more difficult proof in the classical case, but one that actually works in a non-local setting. So I do this. So I move this point up to here, to this point 1, 1. And then I take a capital R, sufficiently large, and I join like this point with this point here, down here, and I do the same here, because then I want to reconnect to the same, say, boundary value, exterior like datum. So this is my new set. And now, okay, I want to compare, now I want to compare the energy, so the perimeter of this set with the perimeter of the corner, okay? Okay, so this is one. So let me just show you the computation in the, for this bottom side, because then it's exactly the same. The picture is symmetric. So this is 1, this is r. So this is square root of r squared plus 1, okay? Oops, sorry. So what I did, first of all, if I move like this, I gain 1. Okay, I gain 1 because here I had 1. Now I don't have it anymore. So I gain 1 clean. What do I lose? Okay, clearly this line here, this segment here, is longer than this one here. But this one is capital R. This one is square root of r squared plus 1. And so if I take the difference, okay, so now I factorize r, and I have the square root of 1 plus 1 over r squared minus 1, I think. And now this is r times something of order 1 over r squared. Okay? So all in all, I have something which is of the order 1 over r. So I lose something, but I lose something that is of order 1 over r. So I gain 1 and I lose something of order 1 over r, which means that if I take r sufficiently large, in total I gain, okay? Because it's 1 minus something of order 1 over r. So I gain, so I lose something here, but not too much to compensate the 1. So this one has shorter perimeter than the corner. And now if I try to redo this proof in a non-local setting, this works. Okay, so it's a more complicated proof of the classical case, but this one works in the non-local setting. Okay, so this was good news. We have some regularity theory in dimension 2. So we can do our nice cover of the singular set. We also have a geometric Harnack inequality. This was done by Xavi Cabré and Matteo Cozzi some years ago. We cannot really use it in the way they stated in their paper, because they do it, so they have essentially a smooth or variational, like distributional setting. We need it in the viscosity setting. And for that, we need to pass through somehow a like capacitary argument, for which we need to know that the singular set is indeed sufficiently small. And sufficiently small means that I need the regularity theory in dimension 2. So I need this n minus 3. Okay, so if I want to be able to use the geometric Harnack inequality, I need the regularity theory in dimension 2. But this can be done, okay? So here we managed to check that basically the geometric Harnack inequality also in the viscosity setting. So we are essentially done, more or less. What are we missing? Well, we are missing a good geometric equation, okay, for W, for the normalized distance between the sheets. So the one with the Laplace-Beltrami plus the second fundamental form, the normal of the second fundamental form. And we need a good regularity theory for this equation, because we want to pass to the limit. And this is what we did with Ovidio and Enrico. And so I'm going to now tell you something about this geometric equation that we obtain. Okay, so the mathematical statement looks like this. Okay, so we have our sets E1 and E2. I have nu, so nu is the unit exterior normal to E1. So again, I am away from the singular set. I have taken a big ball and removed the singular set. And then, so I write E2 minus E1 in this way. So it's x plus t nu x, where x lives on the boundary of E1, and t is in between 0 and this distance function w, for some function w. Okay, now I want to somehow translate E1, because I want them to touch at some point to use the equation somehow, to write the equation. So I take x0 in my large ball away from the singular set, and I translate it in the normal direction. So I take this capital X0. This is the point at which I'm going to write the equation for E1 and E2. And E tilde 1 is also the translation in the same direction of E1. So I'm looking at the equation for E tilde 1. So I'm translating E tilde 1 so that it touches E2 at some point. And this is what we obtain. Okay, so this is the counterpart of Laplacian plus square norm of Laplace-Beltrami plus square norm of the second fundamental form in our set. So this is the difference between the non-local mean curvature of E2 at the point minus the non-local mean curvature of this translation of E1. Now, it looks a bit ugly, but let's try to unravel actually what these objects are. Okay, so first of all, we have some small terms here. So we have the R comes from it's the radius of the big ball, and eta is the size of the covering of the singular set. Okay, so this part is harmless because at the end I will send capital R to infinity, so this will go to 0, and eta to 0, so this will go to 0. And also Leon Simon add some additional terms there that will go to 0 in the end. So this is taken care of. Okay, this object here, G prime is some neighborhood of the singular set, okay, so nothing but that. So this is an integral over the surface, over the boundary of E1, in the, sorry, this is the covering of the regular set in the regular part. And now if you are familiar with non-local equations, maybe you would recognize something there because so if I have some function u, say from Rn to R, I can compute an operator that is called the fractional Laplacian. Say, let me call the fractional Laplacian of order sigma because I don't want to make confusion with S from there. And this is nothing but an integral over Rn of u of x minus u of y divided by x minus y to the power n plus 2 sigma dx dy. And if you look at this term here, this looks very similar to that fractional Laplacian computed at w, at the function w. There are a couple of, at least, of main differences. One is that here I have a nice kernel, an explicit kernel. Here I have a kernel K1, which we will see is comparable to that, but in principle is a more general kernel coming from the computation. And of course, I'm not integrating in Rn, I'm integrating over the boundary of E1. So somehow this is a version in this setting of the fractional Laplacian. If you want, this is what takes care of the Laplace-Beltrami part. So it's the counterpart in a local setting of the Laplace-Beltrami operator. So this resembles the Laplace-Beltrami of W. So this term makes sense. So we are happy to have it there because we were expecting something like this. Then what else did we have before? We had the square norm of the second fundamental form. That term is somehow hidden here. So again, this is some sort of norm of the normal. Okay, so, and this is positive because you can write 1 minus the scalar product as the square of nu of x0 minus nu of x. So this is essentially some sort of Gagliardo semi-norm, if you want, of the normal. Okay, again, it's an integral over the boundary of E in the regular part. So this term resembles the square norm of the second fundamental form. And also it has a sign like in the previous case. So we are pretty much happy with this term and with this term, and also with the capital O. We may not like much whatever happens outside. We don't have control on what happens outside the regular part. But this one was part of this integral here, so we have to somehow take care of it. Okay, so in principle, we may be worried because this was not there in the classical case. Maybe we don't know what to do with it. But actually, it's a good term, and we don't want to know much about E1 and E2 outside, regularity stuff, whatever, because this term has a sign, because E1 is contained in E2. So this is going to be okay for us in the end. It has a sign, so it will, the right sign especially, so it will be thrown away in the end. So this term is also good. So after all, it looks pretty ugly, but somehow it seems that we have more or less things under control here. And so yes, so here are the kernels Kj are comparable with the kernel of the fractional Laplacian. And of course, they are only defined on hypersurface, so we should write these formulas using projections, but let's not do that. Okay, and they also approach up to a normalizing constant, the kernel of the non-local perimeter function. Okay, so we have an equation. It's nice. This is very good news. The problem is, okay, fine. It resembles what we had in the classical case, but it's a bit more complicated. Okay, so it's complicated. It's highly nonlinear. The kernels are not symmetric. So we need some work. We need to do some work to obtain a good regularity theory out of it. Okay, so we need somehow uniform Elder estimates to extract converging subsequences. That's what we need. And this is something that we also did with Ovidio and Enrico. So we wrote it in a, we tried to write it in a kind of general form. So suppose that you have some equation that resembles like our equation with the kernel K satisfying our assumptions. Then we can obtain a bound, like a C alpha bound for V, okay, so the renormalized function, in terms of the L infinity norm of the right-hand side. And here we have the L infinity norm of V, okay? So we have some sort of C alpha estimates. The problem is, the Elder estimates relies on an L infinity bound. So here we have an L infinity bound for V. This is not really good because V is a pointwise renormalization of W. Okay, so so V is equal to 1 at some point, but this can be very degenerate, like when we get too close to the singular part. So in principle, this L infinity norm here is not really good. It may degenerate. It's bad. It's bad to have it there. So we need somehow to have a bound for this L infinity norm of V. Okay, so we need a uniform L infinity estimate, which we can do. Nice. So we wrote it also in kind of more general form. So we have our equation with some assumption, and then we can bound the supremum of V with some structural const, depending on structural parameters, and then we have +1 plus m. M is simply the right-hand side of our equation. And then we have m prime here. Very nice. So this is not still good enough because the L infinity bound depends in turn on an L1 bound, okay? Oops, sorry. So this m prime is nothing but the L1 bound on the positive part of it. So we are still in trouble. So are we just kicking the can down the road? Are we finally actually obtaining something? Okay, we only need an L1 estimate after all, so we are not too bad. And this will rely on the fact that V is bigger or equal than 0, it's not negative, and also it is pinched at some point. And so we can actually do that. So assuming that V is non-negative and that is pinched at some point, we can actually prove that we have a uniform bound on the L1 norm, and then in turn on the L infinity norm, and then in turn on the C alpha norm. And this allows us essentially to pass to the limit. And this was basically the last bit that we needed. Okay, so this is something that I mentioned also before, because we are done. Okay, we still had some small issue to fix, which is to apply the geometric Karnac inequality, we also need an energy bound, because we need to check that the viscosity the viscosity setting actually gives us the geometric Karnac inequality in the distributional setting, which was the one by Cabré and Cozzi. And for this, we need to use a capacity argument, okay? And this we can do because the house of dimension of the singular set happens to be small enough. So for this, it is very important. So while for the first part where we do in step 1, this was not really necessary in the sense that, we want to reduce to a tangent cone by dimensional reduction. Sooner or later, we will do it, even if it means going up to dimension 1. So for that part, we don't really need the dimension 2. But for this capacity argument, we really need the singular set to be sufficiently small. And sufficiently small means Hausdorff dimension n-3. So that was really important for us. Okay, and so I think we come to the end. So with this, basically, we can prove our theorem, and the theorem is like this. So if I have my two S minimal sets in B1, one is containing the other, and they touch at some point, then they must coincide. So it took it took somehow, maybe, I don't know, I can see that they're like 89s. I don't think they were 89. 89 probably counting poses. So it took 89 somehow slides to prove this result. So it's a bit more than one slide, and it was a bit technical, but finally, I mean, the result is true. Maybe less obvious than one thinks. So I will stop here. Thank you very much.
Okay, thank you, Serena. Are there questions or comments? I have one question. Okay, I wait.
Do you think there would be a hope to lower maybe the regularity at least of one of the two sets? Maybe assume that just one of them is minimizing.
Say it again.
I was wondering if you think
Yeah.
there could be a hope to lower the regularity at least for one of the two sets. So not assume, for example, that it's minimizing, that just one of them is. Like the resulting of Solomon White, for example, I think in the local case.
In the classical case, I think you don't need minimality. Like there are some papers by Vikramasekar, I think, where so it doesn't ask minimality, but the equation was enough, but it still had to assume something like on the smallness of the singular set. So I don't know the argument, and also I think he had something that he called like K condition, which means that basically I don't remember exactly, but there were some kind of geometric conditions. So to be honest, I don't know. They are very much like geometric measure theory arguments, and sometimes it's very difficult to like redo stuff in a non-local set. The non-local perimeter doesn't lend itself very well to those type of arguments. But yeah, I think that would be a very nice problem. Yeah, I don't know.
Thank you.
Are there other questions? So my question was if the n-3 sharp, the estimate on the dimension on the singular set, are there upper bounds? I mean, example of a singular set of some codimension.
I think, okay, so I think n-3 is not, I think people believe that n-3 is not sharp, and probably, okay, so there is this additional result by Enrico and Luis Caffarelli that says basically because the classical the non-local perimeter converges to the perimeter, when S is very close to 1, the non-local minimal surfaces inherit the regularity of classical minimal surfaces. So as soon as S is very close to 1, the regularity is up to 7, essentially. So at least when S is large, maybe we can expect the same regularity of classical minimal surfaces. When S is small, is not clear, because when S goes to 0, the local perimeter converges to the Lebesgue measure, so not much can be done there. I think there was a paper by Davila Del Pino and Way some years ago, where they show that when S is close to 0, so they looked at Lawson's cones, and they show that Lawson's cones are stable when S is close to 0 up to dimension 6, are unstable maybe up to dimension 6 and stable from dimension 7 on, something like that. So now stability is not minimality. So let's say there are maybe two categories of people: those that believe that the regularity theory is the same as in the classical case, and those who believe that maybe when S is close to 0, something happens. So maybe 6 and 7 is the right, I don't know, change, but this is not clear.
Okay, thank you for the answer. And if there are no other questions, also we thank again the speaker.
Thank you.
Okay, so the next speaker is Roberta Marziani from the University of Siena, and she will speak about Ambrosio-Tortorelli approach to topological singularities and connections with jump minimizing liftings.
Thanks a lot for the... Can you hear me? Okay, maybe. Okay. Thanks a lot for the kind introduction and for the invitation. So it's a pleasure for me to be here. And I apologize for those who already heard this talk because I presented this summer here in Pisa. But sometimes it's, helpful, at least for me, to hear things twice. So, okay, so this is a joint work with Giovanni Bellettini and Riccardo Scala. And it's the first step of a long-term project whose goal is that of characterizing topological singularities in two different contexts, which are dislocations in crystal plasticity, but also some relation with non-local phenomena which occur when trying to relax the area functional in higher codimension. And we will do that by phase field functionals alla Ambrosio-Tortorelli. So for that reason, I will give a brief introduction recalling the main result by Ambrosio and Tortorelli of the 90s. Precisely, so in the 90s, Ambrosio and Tortorelli considered the following elliptic functional, which depends on two variables, u and v. They are Sobolev functions belonging to the space W12. And the variable v is what we call phase field variable, and is taking values between 0 and 1. Now, the Ambrosio-Tortorelli functional depends on these two, on this pair, and on a small parameter epsilon, which will be sent to the limit. And this functional is given by the competition of three terms. So we have a bulk term, which involve both the variables, u and v. And then we have the second and third term, which together form what we call the modica Mortola term. And here you see there is only the v and the parameter epsilon. And now what they proved is that this functional approximate in terms of gamma convergence the well-known Mumford-Shah functional. Now this functional is defined only on the variable u, and now the variable u is not Sobolev anymore. Indeed, is a special function with bounded variations. So meaning it's allowed to jump. And now the Mumford-Shah functional is given by the contribution of two terms. Again, a bulk term and a surface term measuring, if you want, the area of the jump set. Okay, so usually I propose this cartoon to try to explain this approximation. So this term, let me start by the second term. So when epsilon goes to 0, the v here is forced to converge to 1. However, thanks to this, the gradient of the V can become very large, provided that this happens in a region of order epsilon. Now, thanks to this product here, so in particular, the V can make a transition from 1 to 0 in a region of order epsilon. Now, thanks to this product, where the V is 0, the gradient of the U can become very large. And so in particular can produce a sort of discontinuity in a region of order, let's say, smaller, of order way smaller than epsilon. So in particular, passing to the limit, the V is actually 1, my phase field variable became 1, whereas the U produces some discontinuity. And the price to pay is the measure of the set where you produce this discontinuity. Now, a peculiarity of the Modica-Morton approximation is what we call the volume surface decoupling, meaning that the volume term is approximating the volume term, and the Modica-Morton term is approximating the surface term. Okay, this second remark I want to make is instead useful for what I'm going to tell you next. So usually you take your functional defined on W12, so the U is in W12. However, if you enlarge a bit the domain of definition, you can prove that the gamma limit is the same. So in particular, I require less regularity, so my U is just W11. In order to have the energy to be finite, so to control this term, I require this product to be in L2. Now, if you enlarge a bit the domain, the gamma limit is the same. And this remark will be useful for the rest of the talk. And just for completeness, let me tell you that here it's important to have superlinear growth in the gradient of U. So if you can put any P strictly larger than 1, then the same result holds true. Okay, so this is more or less the introduction about Ambrosio-Tortorelli, but now some generalization. So first of all, things are different if you consider linear growth in the gradient variable. So if you replace this with the gradient of U, then you don't have this decoupling anymore, but you have interaction between bulk and Modica-Morton term. And the gamma limit is more complicated. It's a general free discontinuity functional, which has a counterpart. Indeed, the gamma limit is now defined in BV. And the surface term is not anymore the measure of the jump set, but is something more general. And this was actually studied by Alejandro Braides and Shah. Okay, so of course you can generalize the problem to the vector valued case, meaning that the U now is vector valued. So the V is always between 0 and 1, so scalar variable, because it's the phase field variable. But the U can be vector valued. And this actually has application in fracture mechanics, for example. And so to study theory of fracture mechanics. And actually here are some references for the vector valued case. Okay, these are like the more like the first results in this context, and then after this, a lot of generalization have been provided. Here are just some names. So if your name is not in the list, then it's in the dots. And so discrete Ambrosio-Tortorelli, also the approximation of Griffith energies, homogenization, cohesive fracture, and so on. Okay, so now I'm really done with the introduction. Now I pass to our model. So the model I'm going to consider is actually very simple, and it's Ambrosio-Tortorelli for S1 valued map. So precisely, this is the setting I'm going to consider. So now my domain omega is in Rn. Then I have S1, which is the unit circle in R2. Then I have, again, two variables, U and V. V is always my phase field variable, whereas U is a map from omega to the unit circle. And now to this pair, again, I associate the Ambrosio-Tortorelli functional. But now the variable U is S1 valued. So in order to remember this, I put S1 here. And now the question I want to address is the following. What is the gamma limit? So simple question, what is the gamma limit of this functional? Okay, before giving you the answer, just let me give a naive observation, naive remark, is the following. So I told you the vector valued case was already studied, but this is not a consequence of the vector valued case, since you have this constraint of being S1 valued. And Sobolev functions, which are S1 valued, are special. They have special properties, and which we will see. And so for this reason, we actually got two different results, two different theorems, depending on how you choose the domain of definition of your functional. So remember, when I gave you the introduction, I told you, well, usually you take W12, but if you enlarge a bit the space, then the gamma limit is the same. That's not true if you have this constraint of being S1 valued. So we have two different results. And the first result, it's in the larger class, which means we are W11, so less regularity. The second result is in W12. So in the first case, we have a local, if you want, gamma limit, which is the Mumford-Shah functional for S1 valued maps. In the second case, which is more interesting, at least to me, it's a non-local gamma limit, and it's the following. So it's, first remark, the domain for the gamma limit is the same. So it's SBV for maps taking values in S1. Now, the second gamma limit is bulk term, which is the same, plus a non-local term. And this non-local term, it's given by the following minimization problem. Okay, here by non-local, I mean that it does not have an integral representation. Indeed, so this M2, I call here, is defined as the infimum of the measure of the jump set of what? Of all liftings of the map U having this regularity here. They are now not SBV, but GSBV. And the G stands for every time I truncate the function at any level, I am SBV. Okay, so here I put lift to remember that this gamma limit depends on the liftings. Okay, so now in the following, I'm gonna do some analysis of the second gamma limit, which is the more interesting one. In particular, I'm discussing the topological and the non-local nature. Then I will prove that there exists actually there exists a minimal lifting, and here you can put any exponent p larger than strictly larger than 1, where the p here in the definition appears just here in the class where I choose the liftings. Then I also discussed that this G here is actually it's necessary, since the minimal lifting in general is not in SBV. And then I will also observe some relation with the optimal transport problem and the plateau problem. Then I will discuss or give you the ideas of the proofs of the gamma convergence. And eventually I will discuss some open problems related to dislocations and also to the relaxation of the area. Okay, so the analysis. Okay, so here you see the definitions so that you have it there and you can read them. So first of all, some remarks about liftings. So any lifting of a map U satisfies the following properties. First of all, the modulus of the gradient are equal. Moreover, the jump set can be decomposed in two subsets, the integer jump set and the fractional jump set. So the integer jump set is the set of points where your map U jumps of an integer multiple of 2 pi, whereas the fractional jump set is the complementary. And now you actually have that the fractional jump set coincides with the jump set of the U. Indeed, if your lifting jumps of an integer multiple of 2 pi, then your U does not jump. So the integer jump set does not transfer to the jump set of U. This actually remarks tells us that in particular, the jump set of the lifting contains the jump set of the U. And so the second, so this non-local term is controlled by from below by the measure of the jump set of the U. Therefore, the second gamma limit is controlled from below by the first by the Mumford functional. Moreover, if there exists a minimal lifting for this minimization problem, the one here, then the second gamma limit coincides with the Mumford functional for the minimal lifting. Okay, so this is basic remarks. And now about the topological nature of this term. So I will try to, yes, sure. Yes, you can do that. Okay, GSBV means that every time you truncate the function, so you truncate at any level, then this is in SBV at any level. Yes, you can do that, but in general, that's so you can assume that it's in L infinity, but in general, this will not be a minimal lifting. So we'll see an example where the minimal lifting is not in SBV, but in general is in GSBV. No, this is the definition of GSBV, of the space. Now for this problem here, for this minimization problem, you go below if you enlarge a bit the space here. So it's really necessary to have the G. Okay. Okay, so now the topological nature. I will give you an example. And actually, if you understand this example, you understand the whole point of this result. Okay, I'll try to go slowly. So I have as omega the unit ball in R2. Then I take the vortex map, which is x over mod x, from the unit ball to the unit circle. Now we know something about this map. It's a famous map used in several settings. And in particular, what I know is that it's W1P, where P is strictly smaller than 2, but it's not in W12. In particular, it's not in SBV2. So why I'm telling you this information? Because this is the limit domain. So the domain for the gamma limit. And so it will be useful in the next. Moreover, I know that the vortex map has non-zero degree. So if I compute the circulation on a circle around the origin, this is non-zero. So the topological degree basically is measuring how many times I go around the identity, the origin. Okay, so theory tells us that it does not exist a lifting of the vortex map, which is Sobolev. So the best you can do is to find a lifting which jumps on a curve connecting the origin to the boundary. Okay, now, in the next, I'm gonna modify just a little bit the vortex map in order to get a new map, which now is SBV2. So I gain some integrability in the gradient, but I introduce a small jump. And I do in the following way. So first of all, I choose a as a lifting the standard phase theta, which goes from 0 to 2 pi. So this means that lifting theta is a jump along the horizontal radius of amplitude exactly 2 pi. Now I take a cutoff function which does the following. So it's 0 in the yellow region. It's 1 in the blue region and interpolates from 1 to 0 in the red region. And then I multiply the phase theta with this cutoff. And now what happens? This new phase, which I denoted by theta hat, okay, here I didn't do anything. Okay, here I put it equal to 0. Here instead I did some interpolation, meaning that the jump set now here, so the jump opening is not anymore equal to 2 pi, but it's something which varies between 0 and 2 pi. This means that if I define the modified vortex map using this new theta hat, now this is the fractional jump set, so it transfers to the jump set of the u. So now this u hat has a small jump on this red segment here, but I gained some integrability on the approximate gradient. So therefore, this map here is in SBV2. It has a small jump set, and it coincides with the vortex map far from the origin. So I just modified it near the origin. Okay, well, that's good because now I have some candidate for which I should be able to construct a recovery sequence. Okay, so what we do? Okay, if you know how it works with the classical Ambrosio-Tortorelli, so usually what you do, so to construct the recovery sequence, you just regularize near the jump set. You don't touch outside, but in a neighborhood of the jump set, you do some regularization. For example, you use a distance function or you do modification, whatever you prefer. And then you choose the V, the phase field variable, accordingly. But if you do that, you get an approximating sequence which has the following properties. So this approximating sequence coincides with the vortex map far, so near the boundary. This means that it has to have non-zero topological degree far from the origin. Therefore, this map cannot be in W12. However, it's still Sobolev, so it's in W11. And we can actually construct the V in such a way that this product is in L2. So this construction, which repeats the construction by Ambrosio-Tortorelli, is a suitable recovery sequence for theorem 1. Of course, here you need to be sure that you're to keep the constraint, but other than that, it's exactly the construction of Ambrosio and Tortorelli. And therefore, we are happy with this, and we get the Mumford-Shah in the limit. If instead you want to have the W12 regularity, there is only one way. You need to get rid of the degree. Remember, the degree tells you how many times you go around the origin. And so one possibility is to regularize your modified vortex map, not only near a neighborhood of the jump set of the U, but in a neighbor of the jump set of the lifting. So if you regularize the lifting and then define the U accordingly, in this way you remove the degree, because you don't complete like the loop, but it's in some sense you go back. Okay, the price to pay is that you pay some more energy, and in particular, you pay the Mumford-Shah functional associated to the lifting. And so, okay, this is equal to this, so the bulk term is the same, but for the surface term, you need to pay the length of the lifting, of the jump set of the lifting. And here, okay, in this example, I chose exactly the minimal lifting, so this is exactly the minimum, the mean values of this non-local term. Okay, so that's like the whole point of the result, basically. And now since I mean the title of the workshop is local and non-local, so I'm gonna tell you why we call it non-local term. And the reason is that it's not subadditive if you consider this as a set function. So if you see at any domain omega, you associate the corresponding minimization problem defined on omega. And exactly this example is answering to this, explaining this. So again, the modified vortex map is a small jump here in the unit ball. Now let's say I divide the domain in two subdomains, omega 1 and omega 2. And now I consider, okay, this is actually 1 because it's the length of actually less than 1, but it's like this length here. This is actually 0 instead because here there is no jump. So the U has jump only in this segment here. This means that the lifting is Sobolev, and so there is no jump. This is 0. Instead, this second term here, okay, here it's more convenient to connect, for example. So the idea is that you have to find a minimal connection. So if you connect in this way to the boundary, you pay too much. So for example, you could connect vertical here. So and this shows you that you have the opposite inequality, and so you are not subadditive. In this sense, we say that our term is non-local. Okay, now about the existence. For the existence, we actually can put any power p here, strictly larger than 1. And as we will see, this actually this minimization problem, so the existence of a solution to this, has some relation to optimal transport problem and also to the plateau problem. Okay, so we prove existence using direct method. So direct method means you have to prove compactness and lower semi-continuity. And so here is the statement. So you fix your map U, you have a sequence of liftings satisfying this with bounded measure of the jump set. And then we prove compactness and lower semi-continuity. Well, the compactness is actually a bit delicate. Indeed, what we prove is that for our domain omega, there exists a Cacciopoli partition such that if on each element of the partition you subtract a suitable multiple of 2 pi, then you converge pointwise. And why this? And the reason is that if you have a lifting, you can always add integer multiple of 2 pi, and you will always be a lifting of the same map. But now, since here we are working with GSBV functions, then you can locally add different constants. Okay, so this is the best you can do. And then we have the lower semi-continuity. Let me point out that results in the same fashion are available also in the context of Griffith energies. So here are some names of people who work on that. Okay, so now about why this G is there. So is it necessary? The answer is yes. And now here an example. So let's say I will try to explain the example with a picture. So first of all, now omega is the unit square. And then I construct a map whose lifting satisfies the following properties. So first of all, is not in SBV, and its jump set coincides with the jump set of U, so it's only fractional. Therefore, it's minimal. However, if you also ask for the phi such that, let's say, the complementary of the jump set is arcwise connected, then you also have the uniqueness mod pi, 2 pi. So if you are able to construct a map phi with these two properties, you have your example. And the idea is represented in this picture. So we actually want to concentrate the jump set on a sort of snake, a boundary of a snake, which is given by these red segments, which are concentrating in the origin. And then what we do is to actually define our lifting with constants. Let's say here you put some constants in the yellow rectangles, which are increasing as you are getting closer to the origin, and the same on the blue rectangles. But the constants have to be different. And here you put another constant. It's not important which constant you put. And then in the columns, you do simply a fine interpolation. But now, since this, so from here to here you are decreasing. Instead, from here to here, you are increasing. So this means that here you create jump. So now if you suitably choose the constants here and also the size of these rectangles, you actually can construct a lifting with these properties here. And so you actually have that your lifting has a minimal lifting. It's not in SBB. Okay. Okay, now instead some connection with optimal transport. So here omega in R2. And let me choose a map, Sobolev map, where the exponent p is strictly smaller than 2. Then you can choose such that it's distributional Jacobian. It's concentrated on, it's a measure, and is the sum of Dirac deltas. Let's say n with the positive sign and n with a negative sign. And now you consider the following optimal transport problem. You define two measures, mu and nu. Mu is the sum of the positive Dirac deltas. Nu is the sum of the negative Dirac deltas. And then you want to minimize, you want to kind of transport the measure mu to the measure nu by minimizing the following cost functional. And so you want to find the minimal connection. And now actually what we have is that the cost function is exactly 1. Then this optimal transport problem coincides with our non-local term. And also the solutions are related. Okay, actually optimal transport problem in this flavor have been studied by, for example, Marchese, Massacesi, and Tione. Instead, if now we are, okay, now with this picture, for example, our solution coincides with the solution to the Steiner tree problem. So let's say as a mu, I choose the Dirac deltas with the multiplicity 3 at point A. And as a measure nu, I choose the sum of Dirac deltas in these 3 points in these 3 points, so B, C, and D. And then my solution coincides with the minimal connection, which transports the measure mu to the measure nu. If instead you are in dimension 3, so omega in R3, now you can choose your map U, Sobolev map U, such that its distributional Jacobian, it's concentrated on a curve. So the distributional Jacobian is always concentrated on codimension 2 objects. So in dimension 2, you are concentrated on points. Dimension 3, you are concentrated on, let's say, loops or lines. So for example, let me assume that my line here, gamma, is a closed curve in R3, a smooth curve. And then you consider the plateau problem. So you want to minimize the area over all surfaces having as boundary this prescribed loop. And actually what we have is that our non-local term coincides with the minimal value of the area. And so our solution coincides with the solution to the plateau problem. Okay, so now let me instead give you some ideas of the proof of theorems. Okay, as you might expect, so theorem one, the proof of theorem one is actually very simple, since we can reproduce the argument of Ambrosio and Tortorelli. The only delicate point is to, so you know, when you have to construct a recovery sequence, you usually use a density result. And so in order to have this density result, we need to appeal to some regularity of minimizers for the Mumford functional when your function is S1 valued. The second result, instead, it's more challenging, in particular the lim-inf inequality. The lim sup is actually proved by generalizing the argument which I tried to explain to you for the modified vortex map, the one I explained to you before. So now you have a general map and you try to do this for a general map. So you choose a minimal lifting, which we know it exists, and you modify, you regularize near the jump set of the minimal lifting. For the lim-inf inequality, instead, we have to work a bit more. I mean, there is no, I cannot give you all the details, but I'll try to convince you why it's difficult and what is the main point. So usually the lim-inf is the following. So you have a sequence converging in the corresponding topology, let's say L1, and then you have to prove this inequality. Now, since now we are theorem 2, means that U is W12, theory tells us that if you are W12, you can always find a lifting which is W12. So it's convenient to pass two liftings. So I choose for the corresponding U, I choose the corresponding lifting in W12. And now I can rewrite my Ambrosio-Tortorelli functional for S1 valued maps with using the lifting. So it's the classical Ambrosio-Tortorelli functional for the lifting. Well, if I would know that my sequence of lifting would converge in L1, then I could just apply the Ambrosio-Tortorelli functional and conclude. But this is not true. And the reason is that the liftings can always escape to infinity because you can add integer multiples of 2 pi. Okay, that's why we have to use a local argument. And actually here we can exploit the fact that you have this volume surface decoupling because we are in the case of superlinear growth. So for the bulk term, it's easy because we apply, if you want, Focardi. For the surface term, so in order to show that the modica mortola term approximate the non-local term, we do the following. So we have to prove that these liftings converge in some sense. And so the best we can do is to find, again, a Cacciopoli partition such that in every element of the partition, if you suitably subtract a multiple of 2 pi, then this pointwise converge. But this is not enough because Ambrosio-Tortorelli works if you have L1 convergence. And so for this reason, we need to kind of truncate our functions and then use a local argument, so a Vitali covering argument, and conclude. So here there is some work to do. Okay, so now maybe I give you some ideas of what comes next. Of course, there are plenty of things that can be done. So here I just give you some. Okay, as I told you, the final goal is to characterize topological singularities, such as dislocations in crystal plasticity, or if you want, vortices in superconductors, but also study some non-local phenomena which arise when you try to relax the area functional in higher codimension. Okay, so what are these locations? So these locations are line defects in crystals, which arise from plastic slip. And they can produce very complicated geometries. Actually, I would need another talk to explain you what are these locations. But there are special type of these locations, which are called screw dislocations, which are described by this cartoon. So this picture was actually provided to me by Lucia De Luca. So here you have an original, like a perfect crystal. And then what you do is to deform this crystal by slipping in the vertical direction, but just on one half of the crystal. So here it's, you don't touch it, you just slip on this half of the crystal. And now what happens is that you create a defect in the center. So it's a line defect in the center. And this actually is detected by using the method of the Burger's circuit. So if you draw a closed circuit here, and then you see its image through the map, you see that this circuit is not closed anymore, and the missing vector to close the circuit is what measures the magnitude of the slip, and indeed is an important vector, and we give it a name, we call it Burger's vector. So now, in the case of screw dislocations, where you have this vertical movement, if you want, you can actually reduce the analysis to two-dimensional models, because what matters is just the vertical displacement. And so you can actually define an energy which depends only on the vertical displacement, let's say theta. Now here there are plenty of models for dislocations. I will not cite all of them. I will just focus on a model recently proposed by Lucia De Luca, Nicolas van Goethem, Riccardo Scala, and also by Vito Crismale, where they pass to S1 valued maps. So here they define the U by using the lifting here. So let's say the vertical displacement is scalar. So it's defined from the horizontal cross-section of the crystal, and it goes to R. So then you define the U, which is now S1 valued. And now to this you can associate some elastic energy. And of course, the fact that you produce that you have these defects implies that your U has a singularity, if you want. So its distributional Jacobian, if you want, is non-zero. And so what they actually prove, they consider an energy of this type. So you have a bulk term, which is the elastic energy, plus a penalization term, which has this parameter here, 1 over delta. So when delta goes to 0, this is, penalizing the fractional jump set, if you want. And what they proved, so this is now S1, but this is the Mumford-Shah functional with this penalization for maps in S1. And now what they proved is that if you rescale with the logarithm, so this is the classical scaling for Ginzburg-Landau or for dislocations, then this converge to the mass of a measure mu, which is concentrated on Dirac deltas. And in particular here, the topology is, they prove that the Jacobian is converging to this the sum of Dirac deltas. And now, well, this is a Mumford-Shah functional. Actually, let me say that this is 2D result. So why don't we consider an Ambrosio-Tortorelli approximation of this? So I have both delta and epsilon, and I write the corresponding Ambrosio-Tortorelli by keeping this factor log delta and delta here. And so now what is the analysis? What is the gamma limit? You can actually distinguish between 3 different regimes, depending on the velocity of convergence between epsilon and delta. Let me say that maybe this can help to generalize the result in 3D. We still don't know, but maybe it can be helpful. Let me also say that in this first regime, we expect to recover the result, since it's like freezing the delta and first doing Ambrosio-Tortorelli and then the result, like by Riccardo, Lucia, Nicolas, and Vito. In this intermediate regime, instead, let me do some computation. So let's assume epsilon is delta, then I just rewrite this functional in this way. So here, okay, there is always the logarithm, and here now I have delta square, and here there is nothing. And now I do a change of variable. So f is the product between u and v. And so this means that v corresponds to the modulus of f. Now, if I compute the gradient of f, gradient square, let's say, by chain rule, is given by the square of this quantity. And now, since the double product is null, I have just the sum of the two squares. And now let me look at the functional. So this is the bulk term, and this is this guy here. Whereas the v is the modulus of f. Now, if I rewrite everything in terms of f, and then I note that this is nothing but the Ginzburg-Landau functional. And so this is actually well understood. And for example, many people work on that. For example, let me cite Alberto Baldi Orlando. And actually, from this, we know that this regime is equivalent to this. About this, still don't want to say because I still don't have it clear. Okay. So now, in the last 5 minutes, let me instead comment on the area functional. Okay, so the relaxation of the area functional is an interesting problem since it helps to study the plateau problem in the non-parametric setting. And actually, in higher codimension, it's not clear what it is the relaxation of the area functional, particularly in codimension 2. And for example, so very few cases are well understood as the vortex map and the triple junction function. And the reason is that some non-local effect can arise. And here are just some names of the people who work on that. But let me instead consider a simplified problem. So I consider the relaxation of the area keeping this constraint of being S1 valued. So I have a function from omega to S1, and I define its relaxation in S1 by approximating the area of its graph with the functions which are C1, but take value in S1. Now, this is well understood, very easier problem and well understood since it's a sort of codimension 1 problem, and actually was characterized using the language of Cartesian currents. For example, you can find a reference in the book of Giaquinta Modica Suchek. I have to say that every time for me it's very difficult when I try to understand that formula. And so that's why we propose a different characterization using the language of liftings. So this is in preparation. We actually believe, at least when omega is simply connected, that the relaxation of the area that this quantity here can be written in this way. So you have the absolute continuous part with respect to Lebesgue measure, then you have a Cantor part, and the surface term is instead replaced by this non-local term, which depends on liftings. Let me also say that for that, we also believe there is an Ambrosio-Tortorelli approximation. Indeed, at the beginning, I told you that if you have linear growth in the gradient of u, then you don't have this volume surface decoupling, but you have interaction between the two terms, between the bulk and the modica mortola term. and this produces a more complicated functional. And actually, since this guy has a linear growth, then we believe that a functional of this type approximates the relaxation of the area functional. And we actually think that this might help also to study the relaxation of the area functional really in codimension 2, so where now you don't have any more this constraint. But this is still some vague ideas that we had like a few days ago. And so with this, I stop, and I'll thank you for the attention.
Okay, thank you, Roberta, for the very interesting talk. Are there questions or comments?
For sure you said it, but I didn't get it. So you have two possible gamma limits, one local and one non-local. Which one is bigger? The second one, the non-local?
The non-local is bigger.
Okay. Now assume that you define Ambrosio-Tortorelli for just U and V in C infinity, C infinity, and plus infinity otherwise in L1. Which is the correct gamma limit, the second one?
Yes.
Because in the first case, you are allowed to use more general, and you need to use recovery sequences that are not C infinity.
Exactly.
Okay. Okay, I got it. Thank you.
Further questions? No? Okay, I have a question. And have you ever talked to the case of the problem with values in higher dimensional spheres? You don't have the lifting, but still you have Plateau problem, which is sort of equivalent.
Yeah, I mean, we would like to solve the problem, for example, for S2. At the moment, I don't have ideas, but yes.
Also, maybe with P equal 3 instead with the power of the gradient. Probably should be changed because there are different phenomena, I mean.
Yeah, you're right. Maybe you say that the critical exponent should be. Okay.
But is it difficult, probably?
I would like to solve, but I don't know at the moment.
So if there are no further questions, we thank the speaker again.